You can start.
Good morning to everyone. Welcome to the first session of second day of the 5-day GIAN course on PV fuels and Microgrid, a sustainable energy solution, PVFCMGSES-2024. Today's session will be handled by Professor Monalisa Pattnaik. Here is a brief introduction of Professor Monalisa Pattnaik. Professor Monalisa Pattnaik received her BTech degree in electrical engineering from the College of Engineering and Technology, Odisha University of Agriculture and Technology, Bhubaneswar, India, in 1999. She received her MTech and PhD degree from Indian Institute of Technology, Kharagpur, India, in 2006 and 2013 respectively. Dr. Pattnaik is a recipient of the PVFCMGSES Power System Award, Power Grid Corporation of India Limited, India, in 2013. She joined as an assistant professor in the Department of Electrical Engineering, National Institute of Technology, Rourkela, in 2012, and is currently serving as an associate professor. Her prime areas of teaching and research include wind and solar engine system, hybrid electric vehicles, efficient power management of hybrid energy systems, grid integration issues of RES, machine drives, and power electronics. Dr. Pattnaik has published 19 journals, 35 conference papers, and 5 book chapters excluding the publication during her PhD. Hope you enjoyed the session. Ma'am, is over to you.
Thank you, Chetana, for the introduction. Good morning all. Today I am going to start the first session of the second day of this GIAN course on PVFCMGSES-2024. So, in my today's lecture, I will mainly focus on sizing analysis of PV fuel cell based DC microgrid, where I will be starting with, as yesterday for whole day you have spent with the microgrid, its application, means why we are going for microgrid, the architecture, the advantages, means whole means almost overall microgrid introduction is given to you yesterday by Professor Bansal. So, directly I will start with the DC microgrid, okay, why we are now motivated to go towards DC microgrid. Then I will come to our main aim, that is the PV fuel cell based DC microgrid, the main components of it. Then the sizing analysis of a standalone PV battery based system. So, after that I will explain about a little bit about the sizing analysis of PV fuel cell based system, why we are integrating fuel cell with the PV based DC microgrid system. Finally, I will conclude my session. So, to start with, so first, as till now all of you know the importance of microgrid or the advantages of microgrid, and why what it offers. Basically, it offers the improved energy efficiency, minimization of overall energy consumption, as it integrates the renewable energy sources, it reduced and gives a reduced environmental impact and improvement of reliability of supply and load. So, these are the some of the advantages, and if you will try to jot down, there are many more. So, just apart from this microgrid application, means why we are going for this nowadays, everywhere microgrid, but now we will talk about the importance of DC microgrid. Before that, just I am instead of showing other things of microgrid, I am just starting with the configurations of microgrid. So, as of now you know that based on different aspects we have different configurations of microgrid, but I am just talking about the microgrid configuration based on the type of power supply or the bus it is connected to, the source and load connected to. If it is connected to a AC bus system, it is known as a AC microgrid. If it is connected to DC microgrid, both the sources and load, and the combination of the advantages of when it combines the both AC and DC microgrid, we are telling it as a hybrid microgrid system. Okay. So, but in today's scenario, our whole power system as means is mainly AC based system. We are it is the mainly AC power system we can say, and now in terms of microgrid it is AC microgrid, which is already well established, well equipped, means we have definite standards, means already well explored we can say. So, when I am talking about AC microgrid, it can all the microgrids already sir has told, means we can operate it either in a standalone mode or in a grid connected mode. So, but now again when we have AC already well designed, well equipped and well explored, then again why we are getting motivated to go for a DC based system or DC power system or DC microgrid system. That is my next aim to explain you. So, first DC microgrid. So, the bus is DC and we are connecting the sources as well as the storage and the load integrated to the DC bus. So, it is the DC microgrid. So, coming to the DC microgrid and then the motivation, why we are motivated for this DC based microgrid or DC power system, because of when we are microgrid, we have the components of microgrid as what we have the we can have renewable energy sources and our conventional sources, but mainly in this course we are talking about the integration of renewable energy sources. So, when we have renewable energy sources, we have some sources like means more explored sources which are very already available and well advanced is the photovoltaic or the solar cell, solar based systems, and now we are also exploring the fuel cell based system. Okay. So, which are giving the output, means the output of this PV and fuel cell are intrinsically DC in nature, means that it gives a output. So, what is the nature of, means how the energy conversion is taking place, I am not concerned about that, means I am not explaining those things, how power is getting converted into PV fuel cell, PV or fuel cell based systems. What is the I am just saying it is a source which is giving DC as the output. Okay. And fuel cell basics and details in our next session, means in the second half will be explained in detail by Professor Sarkar. So, just you take it as the output of PV and fuel cell we are getting, that is DC in nature. So, that is as they are DC. So, we do not need any conversion taking place in between. So, we can directly connect it to DC bus. So, it can be, so it is best suitable for a DC based power system or DC microgrid system. Then when you are combining a energy storage system to the DC microgrid, so the energy storage systems that are mostly available are battery and supercapacitor, which are coming under the electrochemical type of energy storage system. They are also DC in nature. So, it gives a better compatibility for DC systems. Apart from this, nowadays the large number of household appliances which are available in for the domestic or office applications, they are available at low voltage DC. So, those are like means you can take the example like LED fans, LED walls, BLDC fans. So, for which are we can easily supply from a or integrate to a DC bus. And apart from this, it gives this DC microgrid provides opportunity for increased efficiency, reliability and gives energy independence. So, these are the reason which motivates us again from AC system. So, we are shifting towards the DC system. Okay. So, obviously, so what are the advantages of this AC system when we are DC system? It does not require any reactive power and also there is no phase synchronization issues because there is no frequency here. So, we do not need any frequency control and there is no reactive power requirement. That is the main advantage. Apart from this, it gives a reduced AC to DC conversion stages and already this point I have told before, that is it is easily compatible with the home appliances which are available at low power level, BLDC fans and LED lights. And also when we are operating at a low power and low voltage level, so it there is no safety issues. So, we can use it comfortably. So, these are the advantages, but whenever we are getting some advantages, nothing comes free. So, there are some challenges when we are shifting from a AC system from our conventional AC based power system towards a DC system. So, what are the main challenges? Because we can say means still now we have most of the, as we are not aware of this DC system, we can go for a DC system. There is misconception because there are many hazard, means it is not well explored, we cannot go for this. So, there is a lot of debate between AC and DC. So, but for some applications still we prefer the DC microgrid based systems or DC power system is giving are more advantageous with better efficiency, more reliability. So, but because of this less awareness of it is not well explored, so we have to make it, means there is a challenge. So, when we are shifting from our well equipped or well explored AC system to the DC system. So, then it is only limited to low power applications. So, we have not, means only few kilowatt range we have explored, it has not gone up to megawatt level. So, there is a way to go ahead with the DC system if we are going for it. So, there are, when we are going for high power systems with high voltage, then there is a need, if the voltage level increases beyond 100 volt, if we are going beyond 100 volt, so we have to go for a proper safety standard, okay, which is not developed till now. Okay. So, there are the correspondingly the regulatory policy and the policy barriers and energy markets are also not well developed for these DC systems. So, hence there is no, means we have to work hard for to get a proper standard and codes for a DC microgrid system. So, these are the challenges, whereas we are getting some advantages here which is again motivating us to go from. So, there is a, so depending on our application, that is what I want to say is, depending on our application we can go for a AC or DC based system, but when as we are talking about in this special, means in this course as we are only focusing on PV and fuel cell based system, so which are giving DC as the output. So, we are preferring for low power applications this PV fuel cell based microgrid system, this DC systems. Okay. So, then coming to the our topic, means that is PV fuel cell based microgrid. So, here I have tried to show in this single line diagram the sources, that is the renewable energy sources I have shown as directly the photovoltaic cell or the solar based system, the fuel cell based system, which is nothing but means it is through electrochemical process it is generating electricity, which is DC in nature, and we have the storage system. Why we need storage? That is because for this renewable energy systems, when it is operating in either in a standalone mode, the storage is must to make the power system reliable. Okay, because this source, especially if suppose there is no fuel cell, okay, we have a PV system and it is supplying the load, and you know at night we have no sun, and during the as it is this PV cell, because of the weather constraints we can have, there is a wide variation due to the solar irradiance variation, there will be variation in this output power. So, when we have more power we can store it by using a storage, and when there is no sun or less sun, then we can use this stored power to supply to the load. So, that is the main intention. So, we have main three, here if you will see we have three sub units. So, that is the PV power generating unit, fuel cell unit and the storage unit. So, storage unit, that is here I have mentioned hybrid energy storage unit, that is in short you can say it as HESS, HESS, hybrid energy storage unit, which comprises of a battery and supercapacitor. So, why battery and supercapacitor, I will come to it late. So, here I am just showing the components. So, we have a PV generating system, what are the subsystems, I will come to it, but photovoltaic, fuel cell, then the storage and the load. Here knowingly I have shown only DC load because it is connected to DC bus, but here we can have another load here which is very upcoming, means for which this DC bus system is very much useful, that is EV as a load, means EV charging system. If you will connect directly here, then charging station which will charge the EV battery, then it is most suitable for that type of system. Okay. So, here this is the single line diagram which is having only islanded operating in the islanded or standalone mode, or you can say it as also in off grid mode. All these are the synonyms. Okay. So, it is operating in off grid mode. So, each component I will talk about and after telling about the grid connected system, when we have this PV fuel cell, hybrid energy storage. So, basically why the another thing I want to highlight that the without fuel cell also actually most of the systems till available is without fuel cell, means we are going for fuel cell nowadays, we are exploring these fuel cell based systems. Okay. So, this will come later. So, without this fuel cell we have PV, and without this hybrid means supercapacitor also we have a single source and single storage, that is also possible. We can have, so here it is not that as I have shown only PV and fuel cell, it is not that we cannot put a wind energy system here which is giving means AC power which can be converted to DC and it can be integrated to DC microgrid. But as we are mainly focusing on the PV fuel cell based system, so I have shown only DC based sources and the storage system, and it is connected to a DC load. For simplicity I have shown it as a DC load. We can go for other loads also, AC load, then we need one inverter to connect to the DC bus, but here DC bus and another load, upcoming load is a EV load we can go for. So, in my second slide, that is in grid connected system, this is PV fuel cell based microgrid which is connected to the grid, that is also possible. So, grid connected, it is called, it is operated in grid connected mode, it is called grid interactive mode or on grid mode. All these are synonyms. Okay, anytime I can use any type of word. It is operated in on grid condition, or it is grid interactive mode of operation, or it is simple way is grid connected mode of operation. So, means we are this DC bus is integrated to the AC bus through one extra DC to AC power electronic converter. Then depending on the bus, as I have shown it as a low voltage level because of the fuel cell configuration I have chosen. So, this I have used a transformer. So, if this bus voltage is higher, then we do not need this transformer also. Okay. So, that is why these are the, so here I am not focusing on this power electronic components, it will come later, but I am focusing on the sources and the storage, means my main aim is to talking about this sizing. So, before that I am telling about the what are the sources and what is the when we are hybridizing or taking more than one source, how it is becoming useful or what are the advantages of it. So, when here if you will see we have these three systems already I have subsystems I have told, this PV power generating unit, fuel cell power generating unit, then the hybrid energy storage system having battery and supercapacitor, and as it is operating in a grid connected mode. So, we need this inverter which is called also interlinking inverter, which is operated in a bidirectional way. Okay. So, that is another story, means which are operated in which converters are operated in a unidirectional way and which converters are operated in a bidirectional way. The battery and the store means the supercapacitor, those are as it is a storage. So, it need to charge and discharge. So, it is a bidirectional way. Similarly, when we are operating in a grid connected mode, so when there is a excess power from PV, so we can send it to grid, okay, and when there is a shortage, so we can take it from grid. So, this also need to be operated in bidirectional way. So, all these converter control and those things will come later. Here I will mainly I will focus on the sizing part with one example I will explain, but these are the components of the DC based microgrid PV fuel cell based system and how we will go for it, the sizing. Before that I will tell about the some topologies for this PV based system, then the hybrid energy storage system, then I will come to when this PV based system integrated with the normal storage, then why we are allowing this or integrating this fuel cell to it, how it will be useful to us. Okay. And here I have shown with our this upcoming means it is already in market, means EV as a EV charging system. So, where we are charging a battery. So, here I have shown. Okay. So, here that is a possibility we can have that vehicle to grid or means DC grid to vehicle means that bidirectional, but here I have only shown for the charging, means any vehicle is coming and we are charging it. Okay. So, unidirectional way. So, because the whatever type of operation you are increasing, so it will also come with a complexity of implementation. So, to make the system simple first, to understand the system, so we are means first taking as a only DC EV is charging. Okay. And this is, but here the storage we are it is either charging, means when there is excess power we are storing, or if there is a less power means from the source, so we are it is discharging to supply to the load. Okay. So, this is about the components of this PV fuel cell based DC microgrid when it is operated in a standalone mode or off grid mode, and this is for grid connected or grid interactive mode or on grid mode of operation. Okay. Now, coming to the, so individually I will come to one by one, what are the classifications and what are the components, again what are the possibilities. So, coming to the PV generating unit. Okay. So, here we have three options, that can be a PV direct system, off grid or the standalone PV system, okay, and we have also on grid system or grid connected system. So, when I am talking about a PV direct system, that means there is no power electronics interface in between, means it is the simplest system. Okay. So, directly you have PV panels, it is doing some operation like it is charging one battery. Okay. So, there is no means there is no control over that, but the system is simple, and so it is directly coupled to the load. So, you can have a also water pumping system, solar based water pumping system, where you are directly without any control you are directly doing the work. Okay. So, there is no storage. So, that means when there is sun or when there is power you are supplying, when there is no sun or nothing you are this system is very, though it is simple, easy to implement, everything is okay positive, but it is not reliable. Okay. Whenever it is uninterrupted power supply we cannot get it without battery. Okay. So, that is the some advantage, it is a simple system, okay fine, but this is we cannot go for it if there is any, okay, in your rooftop if you want some application and you are going for it, but it is not for some during the daytime you are having that power, if there is a rainy season no power, like that. So, this is the PV direct system. Then to make the system more reliable we are going for a standalone PV system, or it is called off grid system, where we are having the storage, and here PV is a single source and I am adding a storage, and the most popular and the simplest one is the battery, which is oldest one, but still it is in use. Okay. Though it is having many other disadvantages, but still we are going for this battery storage system, okay, with some power electronic interface. So, what is the power electronics interface, that will come later. So, then coming to the on grid system. So, here in this grid connected or on grid system we have two options again, without battery backup and with battery backup. Okay. On grid system means we have grid support. Okay. So, that is we have grid support means when you have power from solar you are supplying to the load, if there is no sun or during night time or low sun condition, means during the rainy season you can, if the load is more you can take help from grid, means you can get power from the grid. So, there is no battery here, okay, without battery backup. So, it makes the system simple and less costly because you are using the grid support, but in case of grid outage again you cannot, means you are only, it is similar to that of a standalone system. So, to make the system more reliable we are having the grid support as well as the battery support. Okay. So, we are making the system more complex, but we are making it more reliable. So, we have, this is the classification of the PV generating unit, which we can means in case of design or depending on the various applications, which application you are choosing, you can go for that type of PV system design, okay, and accordingly we will go for the sizing. So, this is the system. I did not tell only about the source and the storage I told, but then when you are connecting it to the grid, okay, and you have the source PV as a source, but which is very intermittent in nature, means it is weather dependent. So, what we need when you are connecting it to grid, or you can operate it also in standalone mode, what you need? We need to extract maximum power. Okay. So, for that we are interfacing a power electronics converter. Okay. So, what are the power electronics converter, what should be the means how will again it is, if it is grid connected mode, then you need another inverter here. Okay. So, this is the overall power system, means when you have the source, and I have not shown the battery here, you just see PV system, grid, and without grid also it can operate, and in between we need a power electronics converter. Depending on our requirement or application, we will choose the power electronics converter. Okay. So, basically application area, it can be domestic level, it can be for industrial means commercial application, or it can be a PV power plant also. It is only means you are not directly supplying the load, you are just generating and sending it to the grid. Okay. So, that is in from kilowatt to megawatt level. So, based on that we have different applications, okay, which accordingly we will design or do the sizing analysis. Okay. So, next, so here if you see, I have shown the same thing, I have shown in a simpler way without showing the PV panel, the first one. So, here I am trying to show a dual stage configuration. Okay. First it is converting, means when it is you are converting means connecting it to a grid or to a AC load. Okay. So, if you are directly supplying here a DC load, then you do not need all this. Okay. So, here, but here the power electronics interface is coming. So, we have two stages why I am saying, first I am converting DC to DC. So, what this DC to DC converter is doing? This is doing the MPPT, means maximum power extraction from solar. Okay. So, and but as I am supplying to the AC load or to the grid, I need to maintain this bus voltage and frequency constant, as well as I will transfer this, I will convert this DC power to AC. So, I need this inverter here. Okay. So, this is the two stage configuration, which already in the previous slide also I have shown with different way, okay, and with different various applications. So, this dual stage means DC to DC, then DC to AC. Okay. But if I will reduce the stage, directly I can convert DC to AC, that is possible. So, that is that I can do with a single stage conversion system, that is it will be I am connecting the PV panel through a control converter, or I can say DC to AC. Okay. So, this is the control inverter, means single stage converter. Directly I have to maintain this bus voltage constant and frequency constant, and also I have to extract maximum power. So, this inverter is doing that. Okay. Both the work it is doing alone, but so but one stage of conversion is means one converter we are reducing. So, obviously the cost will be reduced, but complexity will increase, because the single inverter has to do both the work, means maximum power extraction as well as the maintaining the grid voltage and frequency constant. Either it is grid, if it is connected to grid, if it is a standalone system, then the bus means that VCC voltage need to be maintained constant and you can supply to the AC load. Okay. So, this is the advantage is we are getting is one converter we are reducing. So, cost is also reducing. So, it is giving, and also loss is correspondingly reducing. So, it is giving a better efficiency. So, this is about a single stage means two stage conversion, then single stage advantage. Okay. Then this when this we are going for this PV system which is operated in a grid connected mode, means the just previous one I have discussed. Here what are the type of means different type of topologies we are going for this grid connected PV system having single stage operation. Okay. So, here based on the size, okay, so we can have a central inverter system, means we have a completely one inverter which is supplying, means converting DC to AC, and again we are connecting it to grid. So, the power level we are considering it is from 30 kilowatt and above, means it can go up to megawatt. Okay. So, which can be, so this is high power level, so it can be either directly you can for power plant application you are generating, then converting, means different solar panels in a PV power plant, you are sending it to grid, or it can be commercial application also which is above 30 kilowatt. Okay. So, the central inverter means we have a single inverter which is has to be operated. So, if one system, that system fails, then whole system is out, means that is the main, though we are having a single thing, but reliability is less here. Then going for a string inverter and multi-string inverter, it is in between string inverter when we are saying it is for small residential applications between 1 to 10 kilowatt, we can go for this string inverters, and between 10 kilowatt to 30 kilowatt we are going for this commercial and residential applications having multi-string, means more number of we are having inverters. So, what are the inverter configuration, those details I am not going here. Okay. And for low power, this is basically between 300 watt or 100 watt you can say to 1 kilowatt application. Okay. If you are developing your small power system, means at your home, so you can go for this module inverter. Okay. It is modular in nature. So, but as it is low power, if you want to connect it to grid, again you need a to boost up the voltage. Okay. So, this all these configurations are suitable, means are consist of what, the PV panels which is converting the solar energy to electricity. Then you have the power electronics converter, depending on the dual stage or single stage, we are talking about the single stage here. So, we have only DC to AC inverter here, and depending on the voltage level either you need another dual stage, means the DC to DC converter if you have to boost the voltage. Okay. So, these are the different power converter topologies which is required for a PV system which is operated in grid connected mode. Okay. So, next we will talk about, so this is the brief about the PV system. Then the storage, already I told what are the storage, means there are several type of storages are available, but this electrochemical energy storage systems which is where the battery and supercapacitor are now mostly used because of its obvious advantages. Okay. But these two storage systems, they have the complementary characteristics. Okay. Complementary characteristics in the sense means battery is having high specific energy, whereas the supercapacitor is having low specific energy, whereas high specific means energy or high power density you can say. Okay. So, these are, it is having less life cycle, whereas it is having fast charging cycle, and longer lifetime for supercapacitor, whereas the lifetime lifespan is less for battery. So, that is the reason why instead of going for a single storage, why we are hybridizing or we are going for more than one storage. We are having two storages, means we are combining the advantage of battery as well as supercapacitor. So, that means, so what is the and what are the different that is another thing, means how we will use it, this storage, how we will connect it to or integrate it to the DC microgrid, that I will cover in my next class. So, just I am saying why we are hybridizing two storages, because when we are adding one thing, obviously it comes with the cost. Okay. And also implementation, everything, complexity, everything is coming up, but still as it is giving a better, means it is improving the battery life cycle, it gives a more better efficiency and also makes the system more reliable, because you can say as it is a for high means energy density, the batteries we are going for it. So, means for steady state operation you can say we are going for battery, means when we will that in my next session when I will explain about the power management, I will to show the details about it. So, this battery and supercapacitor we are utilizing for transient operation, during the transient it is supporting. So, the overall capacity of the battery is reducing. Okay. So, that is why we are going for a hybrid energy system. Okay. So, then I will come to the sizing of the this energy storage system, but I will talk about the only sizing of the battery system, because that it is not possible to cover the whole HES sizing, it is not possible to cover in this time. So, let us come to the before going for the sizing of battery, I will talk about the fuel cell. The last means in our, if you will see the previous slide, means each component I talked about the PV system, its component configurations, then the battery, and then why we are making a hybrid energy storage system battery with supercapacitor, what is the need, why we are adding it, then why we are adding we are making the system more complicated, when then in the PV system PV with battery and supercapacitor we are happy with it, but again why we are going for a fuel cell. Okay. It is not that okay it is available, but there is certain advantage, though we are paying for it till now it is not available means available at affordable cost with when we are integrating fuel cell, but in future obviously it is coming up, means this hydrogen based system, where in fuel cell the hydrogen is given to the fuel cell system and it is providing the electricity as the output. Okay. So, here this fuel cell only, but fuel cell giving electricity, you can have also only fuel cell system which is supplying to the load, but it is from literature it is found that it is not only fuel cell based system is not recommended. Why? Because it cannot handle this high means fast change, rate of change, means because of if there is a fast change of load. Okay, it is difficult to handle by the fuel cell system, because it suffers slow dynamic process response due to its slow electrochemical process. It is not like battery, though it is the effect is like a battery, but because of slow electrochemical process you cannot use it only fuel cell system supplying a load, it is not advisable, means that we are getting from the literature. Okay. So, that is why, but when we are adding with a PV based system, when we are integrating the PV HES based system or PV based means battery PV with fuel cell also, it is giving advantages. So, that I will explain with one small example, how why I am saying it is giving, though single fuel cell based system is not advantageous, but when I am adding with a PV I am making it PV fuel cell based DC microgrid system, how it is advantageous. It gives you just note down the advantages, how it is that I will show with the example. Okay. It gives a better system means make the system more improves the availability and reliability of the system, and reduce the means capacity of the means the size of the battery or the HES. Either it is a only battery, then battery size reduces, or if you are HES, the size of the hybrid energy system reduces, and along with the solar capacity. If that I will show with one example. Okay. And it improves the overall efficiency as the power loss of the overall power loss of the system is reducing. These are the advantages when we are integrating or adding another source to PV, another source basically here the fuel cell based source to the PV based system. Okay. So, after knowing it, let us start our main part, that is the sizing of a this PV fuel cell based microgrid. So, before going to the PV means final one, I will explain with a small example where a PV system means PV direct system, how we are going for a sizing. Okay. Standalone system in my previous lecture, if you can go, it is available also in YouTube, you can go for a standalone system which with a power electronic converter, how we are doing sizing. I will talk about the base sizing also, but only PV direct system I want to explain here. When I am saying a PV direct system, I will explain with the help of one example. Okay, you try to understand the question here. Means here the PV system, the PV cell or PV panel is available, which has to charge the battery. The battery size means the rating of the battery is given. So, a 12 volt battery need to be charged, which is having a capacity of 50 ampere hour. Okay. 50 ampere hour battery need to be charged from this solar photovoltaic panel. Okay. Each cell rating is given. Okay. This panel has an open cell which is having a single cell VOC is given. VOC of the single cell is given 0.65 volt. Okay. And it can supply the current, maximum current it can supply 2 ampere. Okay. At maximum illumination, it is the standard test condition, you can say it is at 1000 watt per meter square and 25 degree centigrade at room temperature. Okay. So, at maximum illumination condition, it is giving a VOC of 0.65 volt and the current of 2 ampere. So, and in the second part you see the cell voltage drops by 10% from its open circuit value before it enters. I will show the corresponding IV characteristics also. Before it enters the constant current mode, means battery is charging either in a constant current mode or trickle charge mode. What is trickle charge, I will also tell. So, this battery bulk charge rate should not exceed C5. Do you understand what is this, what is the C rating of the battery? C rating C10, C20 if you have heard, or C2 C battery or 0.5 C battery means what? It gives the charge discharge rate of the battery. Okay. Means if it is C, it is the ampere hour C rating, means it is the capacity of the battery. C capacity of the battery or ampere hour rating of the battery, and this is the discharging time or the charging time. So, if here it is 50 ampere hour is the capacity of the battery and C5 battery it is given. Okay. The should not exceed C5. So, we are considering it is a C by 5 or C5 battery. Okay. So, how much maximum current it can charge? So, we can get it from here. So, this is a 50 ampere hour divided by 5, it is 10 ampere. Okay. So, you need to charge the battery at 10 ampere, but you are having a solar panel which can supply 2 ampere. So, from it we can get how many solar panels we need, that need to be connected in parallel, so that it can charge the battery. Okay. So, that we can easily find out from here directly. If this is 10 ampere is the bulk charge rate of current, and single panel can supply 2 ampere. So, we need to connect 5 panels in parallel, so that it can charge the battery. Okay. So, this is the number of panels need to be connected in parallel. But next point comes, how many panels you need to connect in series, so that you can charge this battery. You are having a 12 volt battery, but in this you have to see each point clearly. Here the important point you need to note is the cell voltage drops by 10% from its open circuit voltage before it enters the constant current mode. So, if you will see here, I have shown the to find out this it is given in this example this IV characteristics of the solar panel, ideal characteristics it is given. So, when the battery is charging at constant, this is the constant CC mode, constant current charging mode. Okay. It should be charged at 10 ampere. So, in the second part it is given the cell voltage drops by 10% of from its open circuit voltage. Okay, when it enters. So, it drops by 10%. So, here the correspondingly if VOC is the cell voltage, then it drops by 10%. So, it is 0.9 VOC. So, this slope we are getting here like this. So, and this trickle charge in the second part, and one more part it is given, the battery bulk charge rate should not exceed C5, that already we have seen, and the trickle charge rate should not be more than 10% of the maximum bulk charge rate. So, what is the trickle charge rate? 10% of the maximum bulk charge rate. Bulk charge rate we have seen it is 10 ampere. So, what is the trickle charge current? It should be 1 ampere. Okay. 10% of 10 ampere. So, it is bulk charge means trickle charging current is 1 ampere, and trickle charging current is what? It is a continuous or slow charge supplied to the storage battery. It is basically, you can say it is a self discharge rate of the battery. Okay. So, which is allowed for this application, it is 1 ampere. Okay. And the battery is overcharged by 5% from its nominal voltage during this trickle charge. Okay. Trickle charge current is 1 ampere. So, when the current is 1 ampere, so battery is overcharged by 5%. Okay. And so, from this graph, if you will see at 1 ampere and during this trickle charging, the corresponding VOC is from this IV curve we are getting 0.99 VOC. Okay. So, this 0.99 VOC is equal to 5% x means it is overcharging by 5%. So, 1.05 into 12 volt. So, this is the 12.6 volt is the overcharged voltage. So, at this point the corresponding VOC is 0.99 VOC. Okay, we are getting from this IV characteristics. So, 0.99 VOC is equal to 12.6 volt. So, what is the VOC of the battery we should get? It is 12.73 volt. So, how many panels you need to connect in series? So, single panel is giving 0.65 volt. So, that is why it is 12.73 divided by 0.6, we are getting nearly 20 panels we have to connect in series. So, this is a sizing of a solar panel or PV system when it is directly charging the battery, a small example. Okay. All of you are clear about this? Then we can see the sizing of our battery. Okay. When we are going for a sizing of the battery, when it is connected to a DC microgrid, basically we have to fix a, and it is I am talking about that is operating in a standalone mode or off grid mode. So, basically depending on the load it is supplying. Okay. So, first you have for the sizing of the battery, you have to calculate the battery current, how much maximum battery current you need to discharge, and then from there you have to calculate the ampere hour the capacity of the battery. Okay. So, first to calculate the battery current you have to fix the load. So, let us consider a 500 watt. So, you can take means the system you are designing to what value, accordingly you can take the wattage rating of the load, means 2 kilowatt system, accordingly you will have different. So, here I have done the calculation taking a 500 watt load condition. Okay. And the battery voltage you can take, it can be 12 volt, it can be 24 volt, you can okay, depending on the voltage means bus voltage and your load requirement you can choose, or battery size means number of battery, though single battery you are having a 12 volt battery, you can put number of batteries in series. Okay. Here I have fixed the battery voltage at 24 volt. Okay. So, what is the current load current or the battery current from the required load I have decided. So, I got the battery current is 22.16 ampere. Okay. And when I am going to calculate, so first I have calculated the battery current, okay, for a 500 watt load, then I will calculate the ampere hour capacity. Okay. So, how it is calculated? Here actually we need some factors to consider. Okay. To calculate the ampere hour capacity, we have to multiply the load current with the K factor, the T factor which is the temperature correction factor, okay, the aging factor which is given by CAF, and the design margin and overload factor. This design margin and overload factor is chosen to be 5% extra. Okay. Here you can, if you want to further make your system more reliable, so you can make it 10% also, normally it is 5% extra. So, this sorry, here I made a mistake. So, it is 1.05. Okay. So, this design margin, and considering the design margin and overload factor 1.05 is multiplied, but edging factor, considering the edging factor, this IEEE recommended one is the 1.25 is multiplied with the capacity of the battery. And the temperature correction factor, we are considering this, sorry, temperature here we have considered it as 1, okay. And the K factor is actually given by the manufacturer, okay. So, which here I have directly shown 2.61 the K factor, okay, which we will get from the next slide. I will show you 2.61 how we are getting. So, this K factor is given by the this graph, which is here the corresponding the cell voltage, and we are deciding how many hours of backup we need and what is the cell voltage level. Okay. So, this graph is provided by the battery manufacturer. Okay. So, for a lead acid battery we have taken here. Okay. This is for 2-hour backup, okay, and 1.75 voltage per cell. We are getting this K factor here as for 1.75 volt per cell. Okay. For different backup duration, if you are designing your battery means battery system for 5-hour duration, then your K factor will change. So, that we will get from this graph. Okay. Here we have taken it to be 2.61, okay, K factor. So, using that I am getting the ampere hour rating of the battery is around 79.2. So, commercially available battery is nearly 80 ampere hour, or if you want to go for little higher, you can go for a 100 ampere hour battery. Okay, exact it is 80 ampere hour. Okay, so that is the sizing of the battery. Then so I have just skipped one thing, that is I am showing hybrid energy storage system, but I am talking about only battery, because when I am talking about the supercapacitor, that is another complicated process, the sizing of the supercapacitor, which I cannot cover within this time duration. So, you can refer, many papers are also available, but we have designed or if you are going for a small system, the supercapacitor size you can based on the bus voltage and the battery voltage what we are choosing, and correspondingly for how long, means for as we are going for a this transient operation. So, for very low small duration we need, so we can fix the voltage level and correspondingly we can take the standard supercapacitors available in market. Okay. So, normal that is we are using one 32 microfarad, sorry 16.2 volt, that is 58 microfarad is available. So, we are choosing 2 for our system. When in the lab you can see we are using 2 supercapacitors connected in series. So, that is giving overall capacitance is 29 farad, not microfarad, 29 farad and corresponding 32 volt. And we are also having 24 volt supercapacitor, that is 100 farad, and we can go for, so depending on your requirement you can go for it. So, but that sizing I have not discussed here. Then coming to the fuel cell, how the advantages of adding fuel cell already I have told. We cannot go for a single fuel cell based system, that also I told, but when we will go for the sizing analysis or design of the fuel cell system, what we have done? We have done a simple example. Frankly speaking, we have not explored much about the fuel cell system, we have just started working with it. So, we have taken a PV based system without fuel cell, PV and battery, and we have done the sizing using this Homer Pro software. Okay. And then we have tried to do the sizing considering the fuel cell, and we have chosen a fuel cell of 1 kilowatt fuel cell system which is available to us. So, fixing the fuel cell system and doing the analysis, and the load is considered to be EV load, EV as a EV charging system, and DC load, okay, a 500 watt DC load and a EV load of 1 kilowatt. We have tried to design the system. Okay. So, this is for design for standalone DC microgrid we have done, and this can be further extended for grid connected also, but the some other procedures we have to follow. So, first we have started with just try to minimizing the cost of the system. So, this is the diagram with considering only without fuel cell. Okay. We have taken a PV with battery system and it is supplying a DC load of 500 watt and EV load of 1 kilowatt, that is peak load, and of the corresponding unit of energy consumption per day is given. So, that we have first simulated in Homer Pro, and correspondingly we have tried to see what is the effect when we are adding a fuel cell to it. Okay. So, here what when we are adding a 1 kilowatt fuel cell system, how it is what is the effect on the net cost of the energy, okay. Then what is the unit of energy consumption, that we have tried to find from this Homer based solution. Okay. So, here what you can see, when this fuel cell single we are not operating it as, so we have battery backup. So, this is without fuel cell system. Okay. So, during the rainy day, so the batteries, when there is low sun, means during rainy season or during night time. So, we have low sun or no sun condition. So, during that, so to supply the load continuously, to make the power system reliable, either you have to increase the PV size, okay, PV panel size you have to increase, or simultaneously you have to increase the battery size also, means the storage size. Okay. And here, and if the storage is not available, also means it is already battery is discharge condition. At that time, when we are adding the fuel cell, we have given a condition, if the SOC of the battery is less than the minimum level, then the fuel cell is turning on. Other time it is we are not utilizing the fuel cell. Okay. So, just doing that, but you can do several analysis, several conditions can be put up, means just minimizing the cost of the energy, that we have seen. Okay. So, in Homer there are many other options also by which you can see. Okay, but we have tried to just give this constant and try to see that when SOC of the battery is going near the minimum, where the fuel cell is supplying power. Okay, during that time. So, just adding this condition, we have the result it gives is shown here in my conclusion slide. The size of the PV, okay, without fuel cell, okay, we need a 4.1 kilowatt power of PV system to supply that 1.5 kilowatt of load, 1 kilowatt EV and 0.5 kilowatt of battery means DC load. Okay. So, and the battery we need, it needs a 24 volt battery, which we need 10 strings, okay, to supply, give a backup. Okay. And what is the cost NPC, or this is also called the LCC, life cycle cost of the battery, it is life cycle cost is around 5 lakhs. Okay. And the average cost of energy, means that is called levelized cost of energy also, it is around 16.57 rupees per kilowatt per unit. Okay. Whereas, when I am adding a fuel cell system and utilizing it during, means this low SOC condition of the battery. So, the fuel cell, the PV system required is reduced to 2.84 kilowatt, okay, and the battery size is where we need only 4 strings of battery. You see how much reduction. So, correspondingly the net NPC or the LCC is also reduced huge, and correspondingly the unit of correspondingly we are getting the this 12.7 point 12 point the cost of the energy battery without, means when we are adding fuel cell to it. So, this is the basic sizing we have done with a PV fuel cell based system. So, that is why we can conclude that the PV, when we are PV battery we are integrating with fuel cell, it improves the availability of the system and as well as the reliability, and the size of the PV as well as battery is reducing use, and so cost of the energy as well as the efficiency of the system also, overall efficiency of the system also improves. So, this is about today's lecture. So, if you have any doubt you can ask, and these are the references. I will share this slide, and with this I can end my session, but if you have any questions you can ask. Online participants also can ask. So, there are several fuel cells. So, what kind of that you can get in the, here we have considered the that is the proton exchange membrane, PVFC fuel cell. Okay. There are several, your question is valid. That is the PVFMC, that is the proton exchange membrane fuel cell. Okay. So, in the about the fuel cells, sir will be explaining in the next half. So, we can stop now if you have no question. Any question? Good morning, sir. Then stop it, you can close. Okay. So, if anyone is having any question also, you can chat, means you can put in the Teams also, we will address it later. Okay. Thank you all. I can go now? Huh? Stopped.
दूसरा ये नहीं एक्चुअली दोनों का टाइटल ये नहीं दूसरा टाइटल गड़बड़ होगा ना कंबाइंड होगा दोनों का स्टार्ट विद another yes actually the title is a little bit confusing, that will correct. So just see what second no not this one. So the previous we will try for this. Play for just because not this. All three are day one.
Day to day are only 2. सर it will download like it. 10 PPT.
डाउनलोड ये व्हाट्सएप ओपन करो
उसमें
आईडी होगा
हो गया छोटा
scan.
इसमें देखो लास्ट वाला पीपीटी लास्ट पीपीटी
13 14
11 12 maybe 3 I share again हाँ नहीं ऊपर जाओ 3 है ये एक है ये दोनों है this one ये डाउनलोड में डॉक्यूमेंट इसको करो इंपोर्ट यहाँ पे डाउनलोड डबल क्लिक करना पड़ेगा अच्छा ये इसमें दोनों है क्या सर
एक्चुअली वो दोनों मैंने सेपरेट कर दिया वो टाइटल का कंफ्यूजन होगा तो वो बनाऊंगा
अच्छा
तो मैं इसको जब फाइनली शेयर करूँगा ना शाम को मैं एडिट करता हूँ
ठीक है तो अभी सर इसमें ही आपका पूरा हो जाएगा ना इसमें ही पूरा सेशन हो जाएगा कि और एक ओपन करना पड़ेगा
वो बाद में इसमें एक चलेगा लेकिन है कि अभी थोड़ा सा लेंथ रहेगा ये बाकी का थोड़ा शॉर्ट रहेगा तो वो मैं भी आफ्टर कंप्लीशन दिस मे बी नाउ इज 2 hours ना so this can last maybe 1.5 hour and then
अच्छा,
little bit I will see and then continue with that
ठीक ओके सर ओके
because all are difficult to just have 1 hour because depending upon
Yes,
time we
yes.
have to be some little bit short some little bit longer
ठीक है इट्स एज पर योर
yeah we can try to manage on day wise topic wise scheduling a little bit difficult
हाँ यस ओके उसको
इसलिए पूरा करता है कहीं ऊपर का नीचे का थोड़ा कट होता है जैसे व्यू ये पूरा
Stable.
टेबल और लगा दिया तो मन लग रहा है तभी कि
ना अभी ठीक है ना सर
अब ठीक है इसमें थोड़ा सा इसको
आगे चलिए सर
ऊंचा कर सकते हैं थोड़ा ऊंचा कर सकते हैं पीछे से
हाइट करना है सर
नोट पैड कर सकते हैं थोड़ा सा इन डाउन एक दो लगा दीजिए हल्का सा ज़्यादा
ओके सर
नहीं अब देखिए ज़्यादा और
ज़्यादा
एक आ रही थोड़ा
डिस्टेंस ठीक है ना सर आगे लेना
थोड़ा और देखते हैं
नेक्स्ट
ये इसको बार को कहीं कहीं आगे पीछे नहीं कर सकते बार को जैसे नीचे आगे इसको साइड में कहीं इतना ही जाएगा ना बस हाँ ठीक है चलो कोई ओके ठीक है
छोड़ो
रमेश
Start. Start. Good morning, everyone. So, participants from physical mode and online. Good morning, all. Welcome to this GIAN program, second day. I will start with this lecture 11 and 12, Microgrid system design and hybrid energy systems for microgrid. And after that, I will present this lecture 13 and 14 separate slides, energy systems of energy management of microgrid system. So, here microgrid system design, as I explained, you can call it microgrid or even the hybrid power system. So, here I will discuss about this microgrid, start with the importance, general introduction. Then here in this mainly we focus microgrid, like say if the microgrid is like in the remote areas. Okay. As we said that it can be connected with the grid or it can be isolated. So, and we are covering several topics and some topics overlap, same issue we speak differently. So, here like we talk about the particularly the isolated microgrid. If you are designing the isolated microgrid, so here in the isolated microgrid, what will be the different components for the microgrid that we are going to design. So, this as you see that what we can have the different components in the microgrid, it can depend upon what are the natural resources available. Accordingly, we can have the microgrid. So, there is one book very nicely written, little bit old, that very nicely talks about the design of wind diesel hybrid power system. So, some part I have discussed from that book, and then of course, I added some research conducted by me and my researchers as well. So, here first talking about the when we are talking about the like say remote locations, isolated microgrids, like still worldwide there are many locations where we do not have electrical connection to the central grid network. Okay. I give example, even our country, not many, but still few locations could be there where we do not have the grid supply. And particularly I mentioned like in the African continent, there are so many locations, significant population still there where there is no grid supply. It can be due to several reasons. The locations could be very remote, where it may not possible to have this execution of transmission line or to have the centralized grid system. The location could be very remote and the community is very less. If you have to construct like 500 or 200 kilometers of line and there are few houses only. So, it is not economically feasible to have the centralized grid network. So, the reason could be because of the remoteness or it could be because of the cost that the centralized grid system is practically not feasible. But still you see where are human being, electricity need is always there. So, as I give example, for example, SADC country in African continents, significant population, around 20%, just have the access to the grid. So African continent, there are so many countries where the electricity situation is really poor. So any power system which can generate, supply power to those locations, we call by several names like the remote, decentralized, standalone, autonomous, isolated power systems. In fact, long back I did my PhD around this topic, dealing mainly with the wind diesel hybrid power system. Okay. Because if you see like say 20 years earlier, PV was not much, PV was very costly. Now of course things changing. So here if you talk about those remote locations when renewable energy was not so popular, so the most common way to supply electricity to those locations was mainly through the diesel generators. Okay. So if we see the advantages and disadvantages, advantage of the diesel generator is that it is very well proven technology. You have the diesel generator, you have the diesel supply, and the diesel generator will work well if the diesel generator is well maintained. Okay. So there are not much problems as far as the electricity generation is there from the diesel generator. However, you see that there are so many issues with the diesel generator. First of all, the cost of electricity produced is very high. This is because of the cost of fuel itself, which is very costly. Then the transportation cost for the fuel. Even think of the remote locations, it could be in the remote island countries or very remote locations. So how the diesel will be transported, even when we have to do the maintenance for the diesel generator. Okay. So sometimes specialized maintenance is required for diesel generators, so that may need the technician or engineers traveling from the cities to the remote areas. So overall, if you add, the cost of electricity produced from the diesel generator becomes significantly higher. Now interestingly, the book I mentioned, the design of wind diesel hybrid power system, it very nicely mentioned this point that when we have the isolated power system, in that case the peak demand could be significantly higher. The book states that it could be 5 times of the average load. So if the peak demand is high and you really want to meet the peak demand, when you are designing the system, you will design the system taking care for the peak demand, also taking care for the future expansion. So in that case, the size of diesel generator would be significantly large. Okay. You have to take care for, because the system is isolated. So even peak demand is there, it occurs for very short duration of time. You have to take care for the peak demand. You take care for the some future expansion. So in that case, the system you design, you can say somehow keeping the sort of backup. So system is, you can say, little bit oversized. So that will produce the electricity which will be further very costly. Okay. So there are these some concern issues that the cost of electricity produced from the diesel generator is very costly, and some other issue what we discussed yesterday as well, that diesel generator very noisy, it produced lot of noise. Okay. And then other issue, it produces the noise, and then other issue, noise, pollution. So these are of course concern. Okay. Like when we have some specific services, okay, some specific services we are dealing, like for example noise example I am giving. For example, where you see that some priority building are there, like say where TV transmission is taking place. In that case, for example, if you have electrical tube lights, so you have this choke. The choke will also produce the humming noise. So they will make provision that all the electrical chokes will be placed outside the room. Okay. So depending upon what kind of application you are designing, so noise could be one of the concern. Same way when we talk about the air conditioner can make some significant noise. So when we see the split AC, part of the AC will be placed outside. So when we are designing the system for what application, it becomes very essential that what are some specific customer needs. So we have to take care for those issues as well. So here cost is one of the major concern, because we will expect that the communities living in the remote areas, poor community, so very difficult for them to afford. So whatever the power system we design, it should not be very costly. So here if along with the diesel, if whatever we can see that what are the natural resources available in terms of wind, sunshine, biomass, micro hydro, whatever different natural resources available, so it should be exploited for the electricity generation. So when we can add the along with diesel generator, if you can add the other types of generation, wind, PV, micro hydro, whatever available, depending upon the availability of the sites. So this system we call it the hybrid power system. Generally a hybrid will have more than 2 types of sources, it can have more as well. So what will be the advantage of this hybrid power system? Obviously it will reduce the cost, then whatever the system sizing you have got, okay, if you have only diesel size will be very big, okay. So its fixed cost and its running cost, it will be very high. So when we add the other resources, so the size of the diesel will reduce, because when we have the large size generator, but its loads keeps on changing. Sometimes the load is very less, maybe say 50%, okay, and then you are running the big size generator. So even its operation will not be an economical one. even the technical constraint that means that generator operation you should have minimum load, also in the coming slides, that for the stability purpose you should have minimum load available on the generator. So basically with the hybrid power system, it will reduce the generator rating, it can reduce the battery sizing, it can reduce the pollution, and moreover when we have the diesel generator, you know, in remote areas, so just very basic electricity is provided, like you see electricity for 2 hours in a day, 3 hours in a day, and just to supply some very basic needs, 2 lighting points, maybe 1 fan, something like that, very basic. But we expect that community should also can have some improved life, so at least they can use some other essential equipment as well. But that will depend upon if we can, you know, expand the size of the hybrid power systems microgrid. So when we have the other renewable sources integrated along with the diesel, so the size of the hybrid power system can be, you know, increased, and the community can be supplied not only just the basic minimum power, but they can be supplied little bit more power, and they can be supplied power for a good number of hours depending upon, you know, how big system we design. So maybe if it can be supplied continuous power, it will be really great. So you can see that in the remote areas, so this hybrid technology is really the great technology. So like say you will see that what should be the solution in the remote areas. So any system you design based on the hybrid power system, which will be really great. So and of course, like at least when we have this remote system, we want to ensure that electricity is there. We want to keep some kind of backup as well. So when we have any isolated system, in that the backup system is very important. So backup system could be mainly through the diesel generator, like we talk about, like in the city itself we are sitting in the city. So what kind of backup we have? Diesel generator. Not only just like say 1 or 2, you will find several diesel generators. Okay. So the diesel generator is generally there. So this hybrid power system will be operated diesel in parallel with the other renewable energy sources, wind, micro hydro, bio, any type of renewable energy sources which are available that can be connected along with the diesel generator, that will form your local grid, what you call this isolated microgrid. So here with the microgrid, obviously how the cost will reduce, because whatever the renewable sources are there, as I mentioned, like the wind, solar, no fuel consumption or free. Even micro hydro, you can also consider that also to be, you know, almost free to some extent. So basically generally you can say no fuel consumption with the micro renewable power generation, and then of course it will increase the the system sizing, and it can help the continuity of the supply along with the diesel. So this way microgrids could be a appropriate solution. Okay, but even we are designing the isolated microgrid system. If it is grid connected, so in case of grid connected system, there is very nice backup from the grid supply. Okay, so we are not too much worried about the backup, but in the remote areas, backup system is really very important. As we see that renewable energy sources like wind, PV are highly fluctuating, so it will affect quality of supply, and as I explained yesterday, whatever power system we have, grid connected system, isolated system, we have to maintain the active power generation between the active power generation and active power consumption, balance between the generation and demand, both real and reactive in the real time system. So in the real time system, we have to maintain the active and reactive power balance within the specified limits. Okay. If this balance is not there, that will affect the quality of supply in terms of voltage and frequency deviation. Here in the isolated power system, managing the voltage and frequency within the limits becomes more challenging task, because here system is significantly dependent upon the renewable energy sources, so which are highly fluctuating. Okay. So the control aspects in case of renewable power systems becomes more challenging task. Okay. So in power system, as I mentioned yesterday, power system control, the frequency deviation are mainly dependent upon the real power mismatch between the generation and demand, whereas voltage mismatch is mainly dependent upon the reactive power unbalance in the system. So how we can achieve the active power balance? Either by controlling the generation. On the generation side, you match the generation corresponding to load. Okay. So we can call it the automatic generation control, AGC. You are controlling the generation depending upon the load from the generation side. Or another option could be that whatever generation is available, you control the load accordingly. You make the control from the load side. It's called as the load frequency control. So as the generation, whatever generation we are making, then load accordingly we control. If the generation is limited, load is more, we have to do some priority scheduling of the load. If needed, we may need to do the load shedding as well. Okay. So we change the load according to generation. So basically we manage the active power balance between the generation and demand. Same way, we have to maintain the reactive power balance between the generation and the demand. So here we will talk more about that. You have to see in power system what elements, what devices consume the reactive power, what devices, what elements produce the reactive power, and then you accordingly you provide the balance. For example, as we know, induction motor will require the reactive power. That reactive power, inductive reactive power, you compensate by providing the capacitor banks. Okay. So, basic idea is that we provide the reactive power support, maintain the reactive power balance to keep the voltage within the limits. Okay. So, here we can have a microgrid. As I said, nowadays we call it more popularly microgrid. Little bit previously you can call it like the hybrid power system, whether it is grid connected or isolated. So, here you can have the different sources of power generation. Okay. If it is grid connected microgrid, maybe diesel may or may not be there. Okay. But if you have isolated, then generally diesel generator will be there as the backup. So, what renewable sources you can have depending upon the availability of the natural resources like wind, PV, bio, micro hydro, etc. So, you can have these renewable energy sources. Then when we have these renewable energy sources, then we also need the converters, power electronic converters. Obviously, load will be there, and to manage the active power generation and active power consumption, we have the energy storage system. Then to maintain the reactive power balance, we can have the reactive power support elements in terms of capacitor banks. Also, we can have a little bit advanced reactive power compensating device like the SVC, static var compensator. Okay. Then of course, you can have other, in modern microgrid, you can have some other, systems like these, some control and management communication systems, as we are trying to standardize, develop, appropriate protocol standards. So, then we are talking about some other issues like the islanding, etc., protections. So, depending upon the size of microgrid, you can have several features. Okay. So, how many these features you will have on the microgrid, it will also depend upon the size of the hybrid power system. For example, I give you an example. If you have got very small size of diesel generator, just very small size. So, for that you will have just some basic functions for the control. But if you have got the really very big size of diesel generator, then you will have more sophisticated controls, because whatever the additional cost incurred on the large size, you can justify that cost. With the small size, if you make the control system very costly, so it does not justify. So, these different components, you can see this reference paper, so very nicely documented. So, when we are talking about the similar way, little bit the different components what we are producing, microgrid, hybrid power system, we have, for example, diesel generator, wind systems. There can be other types of generators as well. So here the diesel generator, what type of the electrical generator it will have? So generally it will have the synchronous generator, because the speed of the generator is fixed. It is not variable like the wind speed. Okay. So whenever we have this fixed speed prime mover, we use the synchronous generator. Then wind, what type of generator we can have? Like say if we use the induction generator, particularly in the remote areas, so the cost of this generator will be, cost of the system little bit reduced, say 5%, 10% overall cost will be reduced. Then you need to have appropriate control system. Then of course you have got the consumer's load. Then you have got some kind of reactive power support. If for example your generation is more than the demand, okay. So if your generation is more than the demand, then you may need to have some kind of dump load, because you have to match the real power generation with the demand. Okay. So excess reactive power, excess real power generation, how you consume to maintain the frequency balance. So you will have the kind of dump load. Dump, as the name indicates, is just like dumping, like wasting, but if you can have some useful means to utilize power, even if excess power is there, if you can find some useful means like space heating or some other application, so that will be great, rather than just like wasting the electricity in terms of like the heaters which do not you use. Maybe you can find some useful means, okay. But end objective is that you match. Okay. Then of course if there is shortage, then you will have some kind of storage system. Okay. So here you will see that we are matching the real power generation with the real power consumption in real time. Same way reactive power generation with respect of reactive power consumption. So actually I am discussing this point, the book I mentioned, I will show the reference at the end, like the wind diesel hybrid power system. Okay. So some points you will find really very interesting, that when we have the wind diesel hybrid power system, even for example think of you have got the diesel generator, if the load keeps on increasing or decreasing, or if you have to for example little bit increase in the load, little bit decrease in the load, so whether you should have frequent on and off of the generator, okay, or you try to have little bit reduce the number of on and off of the generator. If you frequently make on and off the generator, it will cause unnecessary stress on the generator. Okay. If frequent switching on and off, so here you could have basically two operation, as the load is increasing, decreasing, accordingly you are trying to make the generator frequently on and off, or you have this like the continuous operation. Okay. So both will have some pros and cons. If you are having the continuous operation of the generator, your control architecture will be simple, system is little bit more reliable, but obviously it will have more fuel consumption. Okay. Then the other option, you have that intermittent option, where you have the, when you have this several time switch on and off the generator, so it can reduce the fuel consumption, but your control system will become little bit more complex. So basically you can have this like the continuous operation of the diesel generator or intermittent operation. Like some of the quality parameters we keep in mind, whether it is conventional power system or renewable power systems, what quality parameters we talk. Two important parameters we talk: the voltage stability, frequency stability, extremely important, these two parameters, voltage and frequency. Then some other quality parameters we talk in terms of like harmonics within the limits, power factor should be reasonably high. We talk about the balance, phase balancing, electromagnetic interference. So these are some of the quality parameters what we expect in the power system. Now let us little bit discuss about the choice of the generators. In principle, we can have like the three types of generator: synchronous generator, induction generator and DC generator. So DC generators nowadays are not used, because wherever we need the DC power, we can rectify AC power into DC rather than having the DC generator. Okay. So DC generator are now almost obsolete. So in these two options, synchronous generator and induction generator. So synchronous generator we will be using where we have these constant speed applications like the diesel generator. Okay. So as we have the synchronous generator, so in synchronous generator reactive power can be controlled through the field control of the synchronous generator, and of course the synchronous generator will require the synchronization. So it has to be synchronized. If there are, say, in the hybrid power system there are 2-3 generators, so all have to be synchronized for a sort of local grid. The synchronous generators are more costly. Technical terms it talks that it says that synchronous generators are closely coupled device, that is they have low damping, may require additional damping to reduce the turbulence. Okay, these are some of the key aspects of the synchronous generator. Now let us talk about the induction generator. So this induction generator, and as you know, based on the induction machine you can have two types of the generator, one based on the squirrel cage induction machine, other is the slip ring or wound rotor. So the squirrel cage generator is very robust in construction, it requires very less maintenance. So in the remote areas the squirrel cage induction generator is very popular. Even in the small mini micro hydro, the induction generator are popular, and of course they are less costly as well. Okay. And it adds that they are loosely coupled and have the ability to absorb slight changes in the rotor speed while remaining connected to the grid. We also talked about this. Sorry, this first synchronous generators they have the low damping and require additional damping to reduce the turbulence. Whereas the induction generator, they are loosely coupled device, they are more flexible, more robust in operation. They can absorb slight changes in the rotor speed. Synchronous generator, as we will see, that you have to operate corresponding to synchronous generator. Induction generator, you have got some flexibility for their operation in the rotor speed, while still remaining connected to the grid. So, role of power electronics in hybrid power system, when we are talking about this PV integration as well. So, the power electronics role, as I mentioned yesterday as well, is extremely important, using AC DC AC converter for induction generator. The wind turbines can be allowed to operate at the variable speed. So, the operation becomes variable speed operation, and these power electronics converters can be used for improving the quality of power supply. They can reduce the harmonics and then they can improve the power quality. And when we are talking about this like AC DC AC converter, so the wind system operation could be variable, so that can improve the aerodynamic efficiency of the wind turbine. You can produce the more power, you can reduce the stress and it can offer some additional benefits like the noise from the wind turbine from the low wind speed can be reduced by reducing the speed of operation. So, there can be some advantage, significant advantage for the variable speed operation. Now, for example, when you have the diesel generator, you want to make the choice of the diesel generator. Okay, some of the features, what way you will classify, how we are going to select the diesel generator. So, diesel generator abbreviated as DG. DG we also use for the distributed generation as well. So, you have to be careful, how you are using the abbreviation. So, this diesel engine and DG set. DG set is your diesel engine and the synchronous generator. So, it will convert the diesel fuel into mechanical energy in the diesel engine, and then mechanical energy is converted into the electrical energy in the synchronous generator. So, how you can categorize or classify diesel generator based on several classifications, like the type of fuel used in the diesel engine, what is the engine speed, form of aspiration, operating cycle. So, type of fuel can be like number 2, diesel oil, light oil, or you can have the crude oil, heavy oil. So, depending upon which type of fuel is available comparatively on what cost, which one performance is comparatively better. So, that you may consider when you selecting the appropriate type of diesel generator. So, choice of the fuel will depend upon the cost, availability of the fuel, CV stand for its calorific value, temperature conditions, specific engine features. Small diesel generators can use number 2 fuel. Diesel fuel accounts for 80% of the operation cost. Whatever you have this operation cost, so fuel cost is significant, around 80%.
aspiration, what is the aspiration? Engine can be naturally aspirated or turbocharged. So, in naturally aspirated, air is taken at the atmospheric pressure, whereas in the turbocharged, air fuel mix at higher than atmospheric pressure can increase the engine efficiency. Okay. So, this is what we call the aspiration, how this engine is, whether it is naturally aspirated at natural atmospheric pressure you take air, or it is turbocharged. Okay. So, then talking about the operating cycle, okay, little bit more mechanical side, but it is very important to know about these different features as well. So, operating cycle, as you will see any engine, it can have 2 cycle or 2 stroke or 4 stroke. Okay. For example, this scooter we have got the 2 stroke, whereas the car we have got the 4 stroke. So, what are these 4 strokes? Like the suction, compression, then expansion or useful, and then finally exhaust. So, there are basically 4 cycle. So, suction, like for example, if you are talking that air is sucked, then air will be compressed, then when air is compressed, its temperature increases, then fuel injection will be there, ignition will be there. Okay. And then of course, when the fuel is ignited, it will cause the pressure, it will cause the crankshaft to move in the backward direction. So, like this expansion or like the useful stroke, and finally exhaust. If it is the 4 cycle, it will have like this suction, air is filled in the cylinder, then compression, then further expansion and exhaust. Okay. So, 4 operation of the crankshaft. But if you got the 2 cycle operation, then suction and compression like in one, and then expansion in exhaust like in one. So, you see that you can have the like the 2 cycle operation or the 4 cycle operation. If the generator is small, you can have 2 stroke, but the generator is large, you will have the 4 stroke. So, 4 stroke engine performance is better. Okay. Then how you are cooling the generator? So, if the generator is small, it can be naturally cooled, but if the generator is bigger size, it could be forced cooling, it could be forced air cooling based on the fans, or it could be cooled on liquid cooling. So, appropriate mechanism for the cooling. What will be the speed of the engine? Larger engines, large size engines will operate at the lower speed, generally around 900 rpm. Higher speed engines are common in medium speed, and this speed could be something 1200 and up to 3600 rpm. Okay. So, lower speed is generally applicable for the large size engines. Now, what sort of the control, governor control you have got for the engine speed? So, this governor control very important. So, which will basically regulate the frequency. Through the governor control, you can control the fuel input to the engine. Okay. So, accordingly, whether you have this higher load on the generator or less load on the generator,
accordingly you will vary the fuel input. So, this governor will control the fuel input to the generator. So, all type of generators, small size of generator can have this mechanical type of the governor, but the modern large size of generator will have the electronic type of governor. Then of course, the large size generators generally operate in the droop mode, which allowed the speed and voltage of the generator to slightly change with the change of the load. Generally, you will see that our power system have got the droop characteristics. Okay. So, as the load on the power system will increase, the frequency will slightly go down. If the load is lower, frequency will go higher. If the load is nominal, frequency will be nominal. Now, talking about the like this wind turbine sizing. So, like when in the hybrid power system, you have to decide the size of the, talking little bit design of the different components. Okay. So, when we are talking about the what should be the size of the wind turbine, it says that in principle that wind turbine size should be greater than the maximum consumer load. What will be the maximum customer's load, plus you have got some system losses. So, and if you got some kind of like the plus system losses, and of course, like when you are selecting the wind turbine or any size of any equipment, one is that what is based on the design. Then of course, you have to see what sizes are commercially available in the market. Okay. You have to select from those available. You cannot order like your own size based on the calculations. So, you have to see what is available, and when you are making final decision, then cost consideration is very important. Which manufacturer, what size, the cost is also given the due consideration. Okay. Then talking about little bit about the dump loads, like where you have this excess power generation that you are going to dump. So, purpose of dump load is to dissipate excess energy of the wind system. Okay. You are not going to that, you are generating the electricity from the diesel and dumping it. Okay. So, excess energy what you have from the renewables, okay, that you even you have stored your batteries, still the power from the wind is more. Okay. Even you are not running the diesel generator, even the power is more than your load. So, that additional renewable energy you have to dump, like from the wind or even from the photovoltaic. Okay. But obviously, you are not going to do that, you are also operating the diesel generator, whatever excess is being generated, that you are dumping. Okay. So, at least diesel generator simply switch off. Okay. So, the purpose of dump load is to dissipate excess renewable energy from the wind or PV, which cannot be stored, to preserve the stability of the frequency and the voltage. So, this dump load sizing. So, this dump load, what rating you will be selecting. For example, you have got the electric heater as the dump load. So, what should be the rating, 5 kilowatt, 10 kilowatt, what rating you decide. So, in principle, the dump load rating must be able to accommodate maximum input surplus surplus power expected from the system. Okay. How much in worst case scenario? In worst case scenario, how much maximum surplus power you can have it, okay, that you will be dumping. When you are designing something, you consider the worst case scenario. Okay. So, what it could be there, which requires the knowledge that you have got the customer load which is minimum at, you consider that what will be the minimum customer load. Okay. But at the same time, you consider that maximum power is being generated from the renewables. Okay. And diesel generator you are running with the minimum capacity. Okay. So, you consider the worst case scenario to design the dump load rating. Are you following? So, when you are designing, you consider the worst case scenario. And of course, as mentioned previously, that considerations should be given to make use of excess energy in the form of like the space heating, if you can make some useful way of dealing that rather than just wasting the excess energy. Okay. Then like some of the storage options depending upon the application, you can have the different storage options in terms of batteries, lead acid, nickel cadmium, the sodium sulfur, other type of mechanical storage system, flywheel, super conducting magnetic energy storage system. So, you can have various storage options. So, when you are talking about the batteries, so batteries will provide the storage, and they try to, when there is shortage of the power, so they can do the backup. So, in recent time, lot of research going on the battery. We now starting talking on the electric vehicle. So, battery is extremely important. Now, which specific battery you are going to select? You have to give the consideration of several parameters, like when you are selecting the battery, that you give the cost consideration, very important. How much will be the weight of the battery, particularly when you are talking about the electric vehicles. Okay. Then number of charges and discharges, operation it can have, efficiency of the battery, temperature performance, discharge rate, charging rates. So, several technical parameters you have to consider, and then of course cost to finally decide the selecting of the appropriate type of battery. Okay. So, here you can see little bit more classification. Again I give the reference. So, in this year, in this volume, it was kind of special issues, so you can find several interesting papers. So, here you can have a classification for these batteries, like electromechanical batteries. You have the options like the lead acid, lithium ion, this redox. So, there are so many batteries options available. Mechanical in terms of like flywheel, pumped hydro storage, compressed air. Then based on these capacitors, super capacitors, superconducting magnetic energy storage. So, you can have several options available. If we see that for these different types of energies storage, how much capacity it has been installed. Okay. The slide may not be very recent, but like it will give you some idea that what is the largest size of this storage system what we talk. Obviously it is the pumped hydro storage. Okay. So in the conventional power system, in almost every country they try to have few pumped hydro storage, because storage capacity is generally significantly high, could be 500 megawatt, 1 gigawatt. So this size is really significantly higher when you are talking the conventional large power system. Okay. Then compressed energy storage in terms of batteries, you will see the the batteries installation, you see compare with respect to pumped hydro storage. So it is quite lower. Then of course you have to see what are your needs, requirements. So I think this was some special paper on the storage system. Okay. So it talks about some of the common characteristics for the different type of storage systems. Okay. So you have got, for example, ultra capacitors, lead acid batteries, and several other types of batteries. I am not reading all these things in detail, but this is self-explanatory. How much is the specific power production in terms of power, watt or kilowatt per kg. Okay. And then specific energy. So like what you call the power density, energy density, or specific power, specific energy in terms of energy per unit of weight. Okay. Then life cycle. So you have to give consider what will be the how many charges and discharges it can have. So that will decide the life of the batteries, and then the discharge rate and the efficiency for the storage system. So you give the consideration for several number of technical parameters to see that for a particular application which type of storage system could be most suitable option. Okay. This may be little bit old. When you are referring, please try to have the latest information. This the battery technology expanding very fast, so things keeps on changing very promptly. So you give consideration for this density, cost, cycles, charging time, power. So all these technical considerations are given. So these above values, it says that approximately battery technology is rapidly changing, and there are many different types with each categories. So for stationary application, like lead acid is quite good, and for electric cars, maybe lithium ion battery can be appeared to be the good options. But this again you have to consider the various options. Talking about the, like say when you are managing the energy management. Okay, you are managing the real power generation with respect of real power consumption. As we talked about the AGC, automatic generation control, or we talked about the load frequency control. So you are managing
managing the demand. So, how you are managing the load? You can manage the load what we call is the from the demand side. Demand side management, or abbreviated term DSM, demand side management. Okay. So, problem of wind power variability can be tackled by the load or demand side management, rather than to match the generation to the customer loads. Load management involves to vary the load to match the power available. You can have priority switching loading as well. So, you need to consider the load management. Now, little bit mathematics, talking about, if you have to design the generator, very simple calculations. So, rating of the generators, how you decide the size of the diesel generator, some technical calculations. So, how much is the active power demand. So, for example, you can have this active power of the synchronous generator decided by this power consumed by the load, dump load, and then wind. So, wind power will also supply the real power, so that will be subtracted. Even if you have got say photovoltaic, so you can subtract that. So, depending upon what are the different renewable power generation, so accordingly you have the suitable equation for the real power. Same way reactive power. Reactive power, again you will see that in the hybrid power system, which device supply the reactive power, which device consume the reactive power. Okay. So, like the reactive power, if you have this inductive load, so inductive load will consume the reactive power. For example, induction motor loads. Dump load based on the some inductive load, you can have this, and then the wind power. Okay. Wind power, whether it will be this positive or negative, it will depend upon the type of generator. If you have the synchronous generator, it can generate the reactive power, but induction generator, it will consume the reactive power. We will talk more about that. Okay. So, this reactive power from the wind depending upon the type of the generator technology. Okay. So, here it says that assuming that it is induction generator, that is why it is positive. Had it been synchronous generator, then you consider is the negative. So, assuming that dump load have thyristor control, if the dump load is having some thyristor control, it will switch on and off at zero crashing of the voltage. So, reactive power demand for the dump load will be 0. So, what sort of system you are designing, you decide. Then of course, you have the different factors you consider, how much input you have got, how much knowledge you have got, that wind turbine has the converters, what firing angle they operate, accordingly the reactive power
for the wind system, you can determine, as you have this right angle triangle, real power of the wind is known, then tan phi P is equal to Q is equal to tan phi. You can decide the reactive power of the wind turbine, and what is the power factor of the system. Say for example 0.8, maximum reactive demand of the load is a QL is PL 10 phi. Okay. Accordingly, once you have determined the real power of the generator, reactive power of the generator, then as you know P square plus Q square under the root, we can get the apparent power as how much will be the like the kVA or MVA rating of the generator. So, all these simple calculations we go as much data as we have to get the some sort of like the design. So, basically I am not going into too much of detail, but you consider some simple cases with these different options whether wind power generation is more than the wind power generation capacity is more than the load capacity, or it is lower than the load capacity. Accordingly, you consider the different options for calculation for the synchronization. When you are deciding the sizing, particularly in the remote areas, so you consider the rating. So, this way basically I explained the different devices like the dump load. Just you do not say that okay, this dump load, let me have any dump load, because when you are doing the technical design, then we give the consideration for the appropriate technical design. Okay. Now, here actually I did my PhD in the similar area. So, interestingly, for example, we have the hybrid power system. Okay. Now, we as the electrical engineer, we see what type of generators we have got. Okay. What are the different varieties of the electrical system equipment we have got. So, basically when we are talking about the power system control, we are talking about the power system control, load frequency control. We have the significant literature available talking about the load frequency control, AGC, but when you are talking about the reactive power control, okay, because one thing is that in general we used to have the thinking that active power is the realistic power which you are using. We will think that reactive power, imaginary power is not useful. Okay. So, we give the very less weightage to the reactive power, and the reactive power modeling, it was not significantly available in the literature. If you find the books, so not much, particularly when you are talking about this along with this renewable power generation. So, I did maybe around now it's 22 years. Okay. So, here again another interesting point, you will see that when we are dealing this mathematical modeling, as you do the course like the circuit analysis, first year, second year level, we talk about the KVL and KCL. Okay. But when we move to this electrical engineering in the power course, okay, then we talk about the power flow equations. We deal with the power flow equations. Okay. So, this modeling what we developed based on the not on the KVL KCL, but based on the power flow equations. So, here Interestingly, I will go through quickly just to give you a little bit flavor of this very important aspect, that the power flow equations, power based equations for the mathematical modeling for the induction generator, particularly for the synchronous generator you can find lot of literature available, but on induction generator you do not find that much literature available talking about the modeling, particularly for the reactive power control in hybrid power system. So, here as I mentioned that when we are using the induction generator, particularly the squirrel cage induction generator, so it offers several advantages in hybrid power system: reduction of the cost of the generator, overall cost of the system. The generator is very robust. The generator has very less maintenance, and there are several features. So, basically in the isolated power system, the self-excited induction generator is a very appropriate choice. I wrote a review paper long back, you can see around 2005. So, was very popular at that time. I think it has achieved some good citation, maybe 700 or something like that. So, basically some of the issues with the induction generator, it will require the reactive power support for its operation. It will need the reactive power for its operation. Now, induction generator, when you are having in the isolated mode, it is not connected to the grid, then reactive power you will supply externally by means of the capacitor banks. Okay. But if this induction generator is connected to the grid, then you can get the reactive power either from the grid or you connect the capacitor bank along with the generator. If you are drawing from the grid, it will stress the grid. So, there are different options, but the induction generator needs the reactive power for its operation. So, in the when I studied, so mainly you will find that induction generator modeling in previously several papers, it was based on the impedance and admittance modeling, like the equation one you say V is equal to IR, okay, V is equal to IZ, or another is equal to current is equal to I is equal to V into Y. Okay. So, in this we specifically develop this based on the power equations. So, I will not go into very much detail, but you will have like the induction machine, induction generator. Okay. You can see the induction machine circuit you can present in the simplified equivalent circuit, series circuit, parallel circuit, and then you have this equations what we see. Okay. So, I am not going into very much detail. Then we published like one paper talking about this mathematical modeling for the induction generator for reactive power control. Even slides we will provide, but if you need you can ask from me some of the research papers as well. Okay. If any of these papers I am discussing, if you need it, I will be happy to share that additional research papers. Okay. So, in this like the very detailed modeling it was developed. I took long time. At that time I did my PhD part time. In fact, I did my PhD from IIT Delhi with Professor T.S. Bhatti, Center for Energy Studies long back.
So, it is now getting more than 20 years. Okay. And then basically all these very complex mathematical modeling you will see is being developed here. So, you know, the reactive power required by the induction generator. Why this minus sign is coming? Because it will need the reactive power support. Okay. So, here basically all this detail modeling I am not discussing, but you can see that this modeling quite complex, quite detailed. Even you can see how the reactive power of the induction generator will be varying, because induction machine at what slip? If the slip is changing, so its reactive power requirement will be changing. So, we develop this concept what you call as the constant speed or variable speed, how the reactive power will change. Okay. So, we develop this detailed mathematical modeling. Then when you are dealing in the hybrid power systems, then you will have other generator like the synchronous generator attached to the diesel generator. So, you have to have the model for the synchronous generator, particularly what study you are doing for the load frequency or mainly reactive power control. So, you write the appropriate model, deal with the appropriate model for the synchronous generator. I am not going into the too much of detail because of the time constraint, but at least you can get some kind of feeling. Then like this flux linkage equations what we deal. Then if you got the reactive power support, capacitor banks or static VAR compensator, you have these appropriate equations, that reactive power support provided by the static VAR compensator, you have that appropriate equations. So, all these detailed mathematical modeling you have for the individual components. Then you have again in your hybrid power systems. Hybrid power system, you want to have the reactive power balance, which devices are supplying the reactive power, which devices consume the reactive power. So, you try to establish the appropriate balance. For example, here synchronous generator supplies the reactive power, SPC supplies the reactive power, load generally consume the reactive power. Induction generator could be based on the wind or small hydro, consume the reactive power. If you have got the photovoltaic or some other generator, you suitably modify these equations. Okay. Then you deal with the analysis, as we call it, like small signal analysis, small scale signal stability analysis. Okay. So, you deal with the small scale changes, and you go into these mathematical equations. I am not going into too much of details. Then of course, you have got the load, what kind of load you have got. You have to do the load modeling, appropriate type of load you have to select, you have to do the load modeling. Then finally, in the system you have the for the small deviation you place this equation. Okay. Equations. So, basically as you are doing the power equations, as we mentioned, load frequency control. Okay. As you had in the power system, what you have got, the turbine, then generator in the feed forward loop,
then the feedback loop, you are taking the signal from the output side, that signal you are feeding to the input side. So, this forms you the everything you put in the each block you place in terms of the transfer function. Same way here we are trying to place that our reactive power model for these power equations. So, this you develop the appropriate model based on this Laplace transformer differential equations. So, basically you are like say overall model system. I will little bit mention, for example, here you have got your reactive power support device, static var compensator. Then you have got here what you call that your synchronous generator. All these mathematical equations we developed. So, this synchronous generator, with this synchronous generator, what type of excitation system you are considering. You can find in the literature IEEE systems that what type of excitation system you are selecting. Accordingly, you have your this excitation system associated with the synchronous generator. Okay, so this part your excitation system, this part you are seeing as your synchronous generator, and then of course like here you are seeing this like overall balance, here you have this load, then whatever you have got this SVC, that SVC signal is coming here, all this power you are trying to make balance here. You can see that the small deviation in the reactive power generated by the synchronous generator, then reactive power, small deviation in the reactive power of the static var compensator. What you have the reactive power consumption by the induction generator, that is why it is coming with the minus sign, and the reactive power consumption by the load. So, how much is the small scale deviation in the reactive power? Okay. So, you develop the appropriate model, use any techniques, can develop this in the MATLAB Simulink, or you can have appropriate program how you develop. So, this was the case when you consider this like the constant speed, when you have the like this, when you consider the effect of variable sleep or speed. So, in that case you have this additional quantities to show the effect of variation of this wind speed, So, like here you can see that what you see for this induction generator in this constant speed, but in the another slide you will see that to consider the effect of variation of the wind speed, accordingly the slip of the induction generator will change and how the reactive power change will be there. Okay. And then of course you analyze, get the results, do the simulation for the small deviation, for this voltage and so many parameters. I am not going into the detail of that, but I will just refer like some of the some key publications, if someone is doing the research in this similar area. So, based on the research we did it for PhD, then some additional research. So, we published a book, small scale analysis for isolated hybrid power system, mainly dealing with the reactive power control, but little bit added for the frequency control. Frequency control you can find lot of literature, but reactive power you will see this sort of modeling you do not find that much frequently. Then some papers I mentioned, one this paper, then another paper, very detailed paper published in IEEE transaction on industrial electronics, automatic reactive power control for isolated wind diesel hybrid power system. And sorry, this book is already there, same book. Then this book I was mentioning, the wind diesel hybrid power system, it is quite old, but you may see that now you can have, this is not only the book, you can have some other book as well, like little bit some of the points I mentioned. So you can find some book dealing with some kind of design, so which can form as some good reference. Then as I mentioned, in this electric power component system, there are sort of special issue now, although it is little bit old, but you can see the microgrid architecture, controls, protection and demonstration. So this way we are just end of this session. End of this session, it took little bit longer, but I wanted to go a little bit more pace with this session. So we will just stop for this session. Maybe quickly, if anyone has, please, any questions from this physical or online participants, please feel free if you have any quick questions. We have little bit time, so any questions, please. Anyone doing the research closer to these areas? If no question, then we will probably take short break, and then maybe someone talking? Yeah, question, yes please.
Yes, sir.
Yeah, speak please.
Yes, sir. Myself, B, sir. I just want to know from you that is there any potential, what is the potential of research in the automatic generation control of an isolated system of renewable energy sources?
Yeah, so it's very good question. In fact, the isolated power system, okay, still as I mentioned, still there are several locations worldwide where there is no grid supply, and particularly we are talking about this optimization, developing the appropriate standards, and you will see that the frequency control is one of the key aspects of the power system control, particularly in the isolated system, because here both the generation and load are changing. Wind speed is varying, all these like input conditions are significantly varying, load is also changing. So making the balance with the active power generation and demand, managing the frequency control, it becomes quite challenging task. And when of course the technology is changing, the battery storage technology is changing, storage system is changing, we are getting the different power electronic converters. So as I mentioned in the yesterday lecture as well, that you will see that the research being conducted in electrical power systems, most of the research revolving around the microgrid. It could be isolated, it could be connected with the grid. So in recent time, this is really one of the very hot topic.
But in the isolated area, if we are going for the renewable energy sources to supply the load in the isolated areas, then then the supply of the reactive power demand will be quite expensive. We can say feature of that unit.
Yes, so that's very important. In fact, you know, the point what I explained, because you know when we are doing, say, for the like little bit from the academic perspective, then we go more scientifically, more detailed analysis. Okay,
Right.
and of course, you know, depending upon, you know, how big is your system. If small system, then we don't go into too much of detail. As I give you example, if you have like for example small 5 kilowatt diesel generator, what sort of control it will have, or one generator you consider like say 1 megawatt capacity. So how much control architecture will be there? So it will depend proportionately. If it is a bigger system, the complexity will increase. We will go more careful in design of that because it involves significant cost. So you go more deeper into that analysis, particularly if your isolated system is quite bigger. Sometimes you think that it is a kind of theoretical questions. Let me share little bit my practical experience. I previously worked in the Fiji Island.
Right.
So Fiji Island, small island country, having the very small island country, population less than 1 million. Okay, very small country, population less than 1 million. So there are 2 or 3 main islands, but if you see small islands, there are too many. So main island, what we call, have basically the electricity supply, you can call it the grid supply. Okay. So in that, at that time mainly it used to be the supply, but you will see that in that significant power generation from the diesel generator. Okay, small country, now I think not very big, maybe around say 400 megawatt will be the total installed capacity, very small because the population is very less. So the diesel capacity is significantly higher. I have some slide, but I can show you. Diesel generator capacity will be significantly higher, maybe say around 40%. So out of 400 megawatt, the 40%, so around 100 or 150 megawatt diesel generator. Okay, so which is, you know, significant. You will see the diesel generator size like in the range like say 10 megawatt, 20 megawatt. Okay, so which consume significant fuel, significant cost. So in that situation, you really need to consider all these, you know, detailed analysis, detailed calculations, even reactive power support, frequency control, what we mentioned. So I hope you are following my point, please.
Yes, sir.
Right? So there could be some you know, specific cases where the, you know, system sizing could be really very big. Although the course talking about the microgrid small size, but yesterday I said that, you know, we are not just focused only microgrid, but renewable power integration as well, and renewable power integration in terms of like this PV farm, wind farm, to have this more and more renewable integration. So thank you very much for very interesting questions. Yes, please continue.
Yes, is there any example in the world where there is a DC microgrid system only? Hybrid is there. There are many applications. Have many arrangements are there with hybrid microgrid. But
Yes.
is there any example in the world with DC microgrid only? Pure DC?
Some of the example I showed you yesterday, I don't recall exactly, but maybe probably we can try to search and find out. I can let you know if I have a relook on the literature.
Yes, hybrid, there are many examples are there for hybrid, but for
Yes.
small loads, if there any DC microgrid, then find out what is the cost involved in that.
Yeah, so maybe I'm not sure, maybe some of the laboratories, small or demonstration purpose, they might have developed.
Yes, that is.
Yes,
that is.
Yes.
Yes. Thank you so much.
Thank you very much. Really appreciate it for some good queries, questions. Yeah, please. So we have maybe little bit time. I think I don't want to start this small topic just few minutes and then stop. So please feel free to interact, ask any type of question, technical, anything, personal, anything you feel. So interact, chat. Okay. I hope some of you know me. Attending online, physical, you might have heard my name. I'm sure some of you might have, yes, you might have come some of our research papers. So please feel free to talk if you have any questions. Okay, if there are no questions, we are finishing probably little bit early. So we'll try that. We'll try to join little bit earlier, or at least in time, so that in the afternoon session we have little bit more material, but we'll try to cover timely. Thank you all. So we again meet as per schedule after the lunch break. Thank you all.
Thank you.
Thank you much. Okay, good afternoon. So now we are going to discuss energy management system of microgrid system, how we are going to manage the energy in the microgrid system. Okay, so I will talk little bit about the general introduction about the microgrid, how we are going to manage the energy from the generation side, how we manage the energy from load side. This energy management system could be a centralized system, or it could be a decentralized system. And then how we manage from the load side, the we can control this energy from the load side. We can prioritize the load. If needed, we may need to do the load setting. So, I will speak very briefly about this, some theoretical aspect. Then I will discuss briefly one research paper written by my past PhD student, like say how we do the economical optimal load management of microgrid system using energy storage system. So, I will just try to briefly discuss, as we will have little bit time constraint. So, I will try to be little bit short, but I will provide the full papers. So, if anyone is more interested, you can go into the detail. Okay. So, some of the general things, like what is the basic function of energy management system. The function of energy management system is to optimally allocate different energy sources to the customers, along with the integrating sustainable power sources without compromising reliability, security, safety of the system. So, basically energy management system optimally allocate the optimum allocation of the different renewable energy sources, mainly using this sustainable power system, ensuring the reliability, security and safety of the system. So, in energy management system can monitor, supervise, optimize, control the customers' distribution, transmission and generation facility. So, this energy management system is we see that grid is evolving complex network with the integration of electric vehicle, renewable energy storage systems and renewable energy sources, energy storage systems and many more factors. So, this energy management system becomes more complicated with this integration of these renewable energy sources, storage systems, electric vehicles. So, it gets more complication. However, with these new tools, techniques coming up, like the IoT, Internet of Things, machine learning, AI techniques. So, this energy management system is getting popularity and simultaneously helpful for the efficient functioning of the energy management systems in the network. So, similar terms like in the past, you would have heard SCADA, supervisory control and data acquisition systems. So, all these things like build up from this previous approaches with advanced features. So, some of the function what it can do, it can give you some clear idea about the energy cost involved, can optimize, monitor electrical parameters for reduction of cost, can plan for future planning based of the consumption patterns from the energy management system, can meter the energy consumption and collect the data, kind of this smart meter function, and can quantify opportunity to save the energy, where it can save the energy, and it can monitor the progress for saving of the energy. So basically overall quite intelligent platform, this energy management system, that what it can do. So it offers several advantages of energy management systems, offers a cost effective solution. Human intervention is minimum, so human these errors in data collections are minimal, and then it is easy to configure and maintain, and helps to identify inefficient electrical equipment, can deal with the maximum power demand analysis, facility of viewing the real time electrical data and energy reports over intranet or internet, has the provision of the graphical display of the energy consumptions, and can alarm for some unexpected events as well. So, some of the objectives of energy management systems can be, in terms of that it can have a single or multiple objectives. When you want to optimize, you can have like the single objective or multiple objectives, which could be technical, economical, techno-economic, environmental, and socio-economical. Because now the research what we are conducting, initially we mostly focused on the technical, then we thought that technical is not sufficient, we should also give the consideration to economical aspects, and then consider environmental aspects, the social economical aspects. So all these little bit interdisciplinary area becomes extremely important when we are conducting research, to make it practical research, the research which could be adaptable by the society. So considering, in addition to technical, economic, techno-economic, environmental, socio-economic, so all this becomes extremely important. In next presentation I will show that one of my PhD student, how he expanded research considering these different aspects. So basically with the integration of these electric vehicles, renewable energy sources, without proper coordination, it can cause the system to deviate from the intended performance. Technical objective of the energy management system can include power quality, effective performance, degradation of the transformer and other equipments, cables, and its consideration will provide better performance of the system, better power quality, improve life expectancy, reduce maintenance and downtime. Economic objectives refer to the economic aspect, as we know that reducing the total operating cost of the energy, cost to the customers, profit, maximization, etc. So, all these aspects related with the cost minimization, profit maximization. Environmental objective, as we know, will cover the greenhouse gas emissions minimization, where the different fossil fuel based generation, mainly utility or distributed generation, and renewable energy sources are scheduled to achieve a low carbon footprint. So, basically environmental aspect, our emphasis is to have this more and more power from the renewable and sustainable power generation to have this minimum emission as possible. Socio-economic objectives are considered, where economic activity is shaped by social process, which includes various programs in which end users, aggregators, agents, network operators take active participation to achieve the best economic outcome. This, for example, I mentioned this social aspect. Any technology is there, okay. So, how the society is maintaining. In the morning class, I explained you about the microgrid, okay. So, I give a practical example when I was in Fiji Island. So, basically their technology is there, okay, that we have the hybrid power systems, microgrid power systems. The government can supply these microgrid systems to the remote communities, no major problem about that, okay. But regular maintaining of this microgrid has to be done by the local community. If it is very much remote, okay, it is chances are very minimum that people from the city or town will go, and just will operate it, okay. So, basically the community has to be trained how the community is going to operate the microgrid system. So, there a proper, it is not only just the technology, but how the normal operation of the microgrid system will be done, and on daily basis how these duties will be arranged, so that everyone has the responsibility to operate the microgrid system, okay. Not only then the question will come, then the community is using this microgrid system, so how the revenue will be collected, okay. All these aspects are extremely important, more than the technical aspect. If there is no proper coordination, no proper understanding how this microgrid is going to be operated, how these regular basis duties will be assigned, how it will be operated and maintained. So, if that is not done, in Fiji Island I am sharing the example that after few years the microgrid system could be unfunctional. It will not because of this technical reason, but more of because of this like this social reasons, that if there is no proper care, no proper schedule, no proper arrangement, then how this microgrid will be operated and maintained. So, this sort of factors becomes extremely important rather than technical, that how this microgrid will have the day-to-day operation, its fuel management, little bit maintenance, general maintenance. So all these things have to done by the local community. If there is something which requires highly specialized job maintenance, then of course it can be arranged at some specific period of time, but regular operation and maintenance has to be done by the community, and community has to be properly trained. If that is not the case, then the microgrid system can unfunctional after short duration of operation. So these sort of aspects are extremely important, and due weightage, proper documentation has to be done, how this community will be trained, how they will operate, even some logbook, how it will be operated and maintained. Even when we are operating any electrical equipment, could be transformer, generator, we always keep the logbook to have the regular readings. Okay, maybe hourly basis. Even sometimes someone miss for 1 hour, at least in 2 hours it will be taken. So this regular operation and maintenance, proper procedure, it is extremely important. Okay. So so all these things, like we are more focused about the technical aspect. You will see that in some other areas or some related to some other journals will be there, which will consider technical plus economical plus social aspects. So all these aspects are very, very important, for this final consideration as a product. So the benefit obtained from the social welfare based program is shared among all the players, including the end users. Like if you have any equipment, any device, okay, how nicely designed, at the end, if community does not accept it by heart, it can may not be very successful. Okay, for example, some device or something like, for example, solar cooker or solar water heating. Okay, so basically little bit effort is required. For example, when you have to cook it, you have to place in the sun. Okay, little bit inconvenient, you have to wait for some time, but sometimes people are impatient and say, no, this will not work. Right. So basically the practical and social aspect is very important. Even the solar water heating system, like if your bucket of water you keep in the sun, maybe little bit it can work, but sometimes people say no, very difficult, we don't want, we will be busy on mobile, we cannot do this thing. So what I mean, that if society doesn't accept, does not tune, if no proper encouragement, no proper training is there, and then it may not work well. So whatever technology is there, we have to motivate, we have to encourage people so that they can really get benefited from this technology. And then as I mentioned that energy management system, it can be characterized, it could be centralized or it could be decentralized. You know, like how we are managing you know, electricity in the grid, in the conventional power system. We used to call this like the national control center. Okay, that energy throughout the nation, it will be controlled in the, you know, center. Then we call it like, say, few regional control centers. So this way, like you have the centralized control, then decentralized control. Okay, so there are different steps involved. So it is characterized by the like the central controller with obviously high performance computing unit and a dedicated secure communication network to manage the utilization of energy. How the distribution of the energy will be there, how this energy management will be there. So this centralized control provides optimal global performance, and it has fair share of some demerits as well. All the information is gathered, handled at one place. The computational burden increases, especially if large number of assets are to be controlled, okay, thereby making this control structure little bit less effective for the real time communication requirement, because all this huge amount of data has to be processed at one centralized process. Of course, we are putting our best efforts, secured connections and high performance computing. Still, because of the huge volume of the data, huge information to be processed, so it can have delay, it can have, you know, less effective. And if this imagine centralized control system fails, so it can be a major issue. So then we see, particularly in respect of this microgrid, we talk about the decentralized approach. So in this centralized approach architecture, it is characterized by distributed processing system with each node having autonomous control capability and peer-to-peer communication with the other nodes. So it will overcome some of the limitations of the centralized architecture by enhancing the expandability, allowing greater flexibility of operation and avoiding like the single point failure. So some of the issues we see in the centralized one, so few can be avoided, and depending on the communication network, it can be fully independent, partially independent, or entirely dependent. Okay. So this is there. Then you will find like the on energy management system, you will find many good reference, and you can have a lot of theoretical aspects. I will share, you know, at the end few references. So rather than going too much, you know, just discussion of the theoretical, you can read any review paper or nice paper. I'll just briefly share like, you know, one of the approach is in fact the research conducted by one of my PhD student, this Steve Madiba. So who did the, you know, economic load management control of microgrid system, like when you want to have this energy management or the load management of microgrid systems. You can have any approach managing the generation through the energy storage systems or through the load management. So basically in this paper, load management control application for an economic load shedding problem. So initially you may have the situation to have this load shedding. So how by managing the generation, even the storage system, how you can avoid this problem of the load shedding, and you can optimize the process, have the economical operation as well. So here the control scheme is based on the coordination for the diesel generator combined with standalone like this microgrid that contains renewable energy resources like the wind, photovoltaic systems, to biomass generation system and energy storage system. The control model minimize the diesel generator units fuel cost, because how we are going to have the optimal operation. Obviously, one objective would be to have the minimum operation of the diesel generator to reduce the cost. Okay. So, it is like one of the main objective into the microgrid, and in this microgrid is basically could have this a plant for example any industry, sugar industry. So, the waste coming from the sugar, so biomass which can be used for the electricity generation. So, there could be any existing system, or you can design any system, the requirement that you want to manage the energy. So, this optimal control scheme has been executed to maximize the energy from the renewable energy resources, and finally increase the, like say, microgrid, if it is operated by independent power producers, profit during the load shedding operation. So, this strategy develops an under frequency load shedding. So, basically as I mentioned, the load like this generation and demand for real power generation and demand, it has to match. But if load is more, frequency goes down. If frequency goes down beyond a limit, so otherwise system will get desynchronized. So, then again you have to have proper scheme that if the frequency is dropping by this, then you have to shed the load, or it can lead to have the blackout situation. Okay. So, basically develops a strategy for an under frequency load shedding scheme to control the microgrid based multi objective optimality. Okay. So, this paper economic operation of load management control of microgrid system using energy storage system, published in the Journal of Energy Storage, Elsewhere journal. So, quite nice impact factor very recently. So, in fact, the student had completed his PhD, then you see once PhD done, they will be little bit relaxed. Okay. Supervisor has less control because student becomes decentralized. So, then you encourage, sometimes you ask some other student and join in the team, help and try to write the paper. Right? So, I ask another student to also get engaged, build bigger team. So, finally managed to publish, and which is good for both from the researcher and of course for the faculty's member as well. So, here basically you will see that in the paper, I will share this paper to you. If you feel interested, you can go in more detail. So, in the literature you will see that when we are having this like optimal operation, in the literature different factors, what different research papers they are numbered here, like what sort of factor they considered in the research. Okay. So, some research paper they will include only this aspect. So, would be your new contribution. So, you can include 1 or 2 additional factors, okay, just to say that this is something extra. So, you will see that the major aspects that dealt are renewable energy resources impact, optimal load shedding control, adaptive strategy for the under frequency load shedding, optimal load shedding control, applied industries, and economic aspects analysis of the load shedding control. So, basically some of the researchers just include like the single point, someone consider like the 2 points, but here in this paper the main author claimed that he has considered all points. I do not know how much he considered, but you know we always say that we are considering something, you know, more. So, this is like the schematic diagram of the system of the microgrid that you can see that proposed under the optimal model based on the under frequency load shedding. So, it comprises of like the wind system, photovoltaic systems, and the battery storage system. Then of course, it has got the 2 biomass generation, and then of course, we have the diesel generator. So, this is a microgrid system. So, just for little bit idea, okay, the sort of parameter what these are considered. So, you have the diesel generator, the rating 1500 kilowatt, so 1.5 megawatts. So, it's not very small system, significantly good. The diesel generator efficiency 0.8, fuel price, at least you know when we are doing research we need the data. Okay, we keep on searching where you can find some good data, okay, either from some research paper or you try to get you know appropriate data, though this becomes very important. So, this then diesel generator parameters A, B, C. So, what are these parameters, like you know how much fuel consumption will be there in the diesel generator. Okay. So, it will depend upon some of the parameters. For example, you have your car, how much fuel it will be consuming. Okay. You have to model it. Okay. Maybe some of the factor you have to consider, like the speed, how much you know speed up and down. Okay. So, this way you have to consider you know some factors like on which this you know fuel consumption will depend. Same way diesel generator, how much fuel consumption will be there, you have to model it a proper equation. Then talking about these batteries, battery capacity 20 kilowatt hour or 5 kilowatt for 20 ampere hours, maximum state of charge, minimum state of charge, maximum 95, minimum 45, charging efficiency, discharging efficiency, charging efficiency 95%, discharging 80%, accepted microgrid system efficiency, frequency 50 plus minus 1.5 hertz, voltage 1 plus minus 0.05 per unit, because in the distribution system we allow the voltage variation of the plus minus 5%. In distribution system, permissible voltage regulation, allowed permissible voltage regulation is 5%, right. In the transmission system, it can be up to 10%. Then we have the biomass generators, both 2000 kilowatt, both 2 megawatt. Okay. Then loads, first and second load, 250 kilowatt. It is basically the industry milling plant. Is the student was from the DRC Congo in the African continent. So he said that I have some plan or some industries there. Is the corn industry. So residue from the corn will be used for this like this for the biomass generator. So it's that, you know, how much corn residue coming, 40, what is the price that you have to consider, $40 per ton, how much will be the calorific value, efficiency of the system. We have the wind system, small wind turbine systems, 5 kilowatt, PV systems, maximum 100 kilowatt, efficiency of PV system 20%. The maximum load capacities, critical and non-critical loads, first and second, 1500 kilowatt, second load 100 kilowatt. Then it also considers in future an additional load to the existing PL3, so it considered for the future load as well. So 1500 kilowatt, significant future load is also considered. Now when you are considering the system, any you know energy management system you are proposing, like you are providing the additional power generation, microgrid. So you have to calculate the cost as well, how much cost it will add. Okay. So for this, like the biomass plant, all these costs are calculated for this biomass generation system. I am not going into the detail. Then you have this like standby diesel generator cost, solar PV system cost, wind turbine generation cost, some contingency. So this way you you know, do the cost analysis. Now the result, I am not going into too much detail about the results, but just I want to give you little bit flavor that what is the outcome. So assessment of the saving for load shedding solutions based on the optimal energy management. Okay, so in these different 3 scenarios are considered. In first scenario, that the microgrid is operating with the initial full load capacity, diesel generator, and the second biomass are not used to compensate the power system. So there is basically no load shedding, and this is there. Then in this scenario 1, for example, it says that microgrid with operating with the first biomass system, assuming to the renewable energy source supplier system, a future load development has been connected. First solution applied is the connection of the 1.5 megawatt diesel generator into the microgrid system. So here we are running the full diesel generator capacity. Okay. So you are seeing that you are significantly using the diesel generator. Okay. So here you are seeing that cost of electricity when you are significantly using the diesel generator, it increases significantly. Okay. So like in the other options, microgrid operating with both biomass generator, you are using the both biomass generators, assuming to be the renewable energy sources with additional future connected load. So you are considering that you will run both these biomass generator, including even in the future that significant additional load will come. You are planning for the future system as well. So here with this scenario, you can see when you are using the biomass system, you can see that there will be significant reduction in the electricity cost, and you can see that whatever the initially you have been using the huge amount of diesel, but now you are means that diesel you can optimize. So basically, if you design the appropriate like say energy management system for a practical situation, okay, how we are going to do that, maybe avoid the load shedding, or how we are going to manage, even you can provide the additional renewable energy sources which can offer green solution. It can reduce the cost, it can avoid the problem of the load shedding. So I was very short in discussing. So here like I just discussed like one of the paper. This way you can find like one more research conducted. So here I also contributed. So I will share this research paper as well. So it talks about the optimal energy management of the small nanogrid, microgrid using the battery storage system. Okay, again you want to manage the energy. Okay, so it could be managed from the generation side, it could be managed even battery through the battery as well. You are managing from the load side, demand side management. And then these are some of the papers talking about the journal paper, journal article talking about the kind of review article. So you can read it if you feel little bit more interested knowing the theoretical background about the topic. I know like one of these the colleague from BITS Plan in India, so they have done few PhD around this optimal energy management system. So this is like one of the another interesting topic. So I have been little bit brief in discussing the topic as we have to little bit cover more. So we just did the small discussion about the energy management system in the microgrid. Please, if you have any quick queries, questions related to this topic, any online student or any physical students, please, if you have any queries, questions, feel free to ask. Okay, if we don't have the question, then we will wait for 2 minutes and then we will move to the next presentation. Please, can you upload the next?
जरूरत नहीं है कंटिन्यूस कर देते हैं इसके बाद फिर इसके बाद नहीं इसके बाद फिर दूसरे करके इसके बाद फिर ब्रेक लेंगे. So you can continue. So in this lecture 15 and 16, which says that stability and reliability concerned in the microgrid system. So here mostly I will be discussing about the reliability aspects in the microgrid systems. So this reliability aspects I am going to discussed. So here again I will briefly discuss this topic, reliability analysis of distribution power system with the integration of distributed generation. Okay. So basically again I supervise one PhD student at University of Pretoria, Dr. Temi Tope Adafrati. So he did PhD with me when I was at University of Pretoria. Like he is one of the great researcher. I'm sharing little bit background because he is really when he joined, he doesn't appear to be excellent student. So little bit, aggressive, little bit more impatient. When he joined, he said, I quickly need the data. I will work on the reliability. So I need the data from the power utility ESCOM. Okay. Then I said, you can approach the utility if they can give you. So he wrote the email or like that. Morning he wrote email. Afternoon he says they have not sent the data. I said no one is just only serving for you that you write the email and they will send the data. This way it will never happen. Like unless you have very strong connections, it doesn't work that way. Okay, I'm just sharing some of the experience. So he tried maybe 1 or 2 days, then he say, okay, I will not do this, this reliability of the conventional power system. Even I suggested that when you deal with conventional power system, the topic will not be very impressive. You will find difficulty in the publication. So I suggest that you conduct the research around the renewable energy integration. Whatever the concept, whatever theoretical background you have, reliability, you analyze with respect of renewable energy integration. Okay. So whatever research we are doing, voltage control, frequency control, fault analysis, so all this research have already been done for the conventional power system. Okay. But with the renewable energy integration, microgrid, this is something newness. Okay. So we are dealing the voltage control problem. It is already solved, but for the conventional power system, with the integration of renewables, how the system behaves. So this becomes something new direction in the research. Okay. So basically here the reliability analysis. So reliability of the power system extremely important. I give an example. I have completed 6 years at University of Sharjah. Okay. So in 6 years, how many times the electricity, failure? I think 1, 2 or maximum 3 times. Okay.
I'm not criticizing. When I was here this morning, early morning, in half an hour, 4 or 5 times, electricity going, coming, going, coming. So that's good that going and then coming as well, right? So basically, this thing is really very important, you know, that the reliability of the power system is there, service is there. You consider any kind of, you know, service, residential to some extent, okay, people will criticize, thoda gali wali nikalenge, but think of the industry, okay. Industrial process will not work, it will have the huge losses. Industrial process, sometime even in the residential system, like say first time when I came, you know, I was there, my wife was there. So we trapped in the lift in 50, you know, years first time. Did you had anyone experience getting trapped in the lift? Any online, please? Okay. So, but it is quite feasible, right? It is quite possible. And some person, like, you know, you think of. So, by the way, you know, you have good luck, you can come out in few minutes, otherwise things can be really, you know, big problem. So even my wife will be scared, she will say, okay, 5th floor, I will just go by walk. So these few things, you know, the reliability of the system, that electricity is extremely important. Any operation you consider, okay, sometime it can be, you know, safety issues, threat to the human being. So reliability of the power system really extremely important. So I will just try to discuss, you know, some part, but when I talk, I don't just only speak only technical. I little bit chat here and there. So you feel happy about that? I don't know. So here, for example, what are the main challenges in the power sector? How to design a system that will have capacity to supply electric power to its numerous customers economically with an acceptable degree of reliability. I will show you some of the parameters what is meant by acceptable degree of reliability. Reduced cost of energy. You want to reduce the cost of energy, minimize greenhouse gas emission, reduced annualized cost of the system, reduce maintenance cost, reduce fuel cost. So several aspect, reduction with the cost aspect means the economic operation, okay. And then of course reduce the emission, the 4 objective in the previous slide we were talking. So something like that, you can have multiple objective, So your microgrid could be comprising of your renewable systems, wind, PV, bio, whatever you have. Then diesel generator, load could be residential buildings, etc. So here again in the literature you can see that he has published several very high quality journal publication. I'll just share the experience, okay. So basically just to encourage our young researcher, that he published several high quality journal. You can search his this Google Scholar page as well, okay. So he did PhD with me, I think during 2017, something that he completed, 17. So when he was associated with me, I also said that please publish in high quality journal. Okay. So, he maintained, still he is doing research. So, whenever he will publish with me, he will only target high quality journal, but when he does on, then any quality journal. Okay. So, even I do not do anything in the research, but I just only advise, mentor some of the broader parameters, that the quality is extremely important. Okay. Research is same, but where you publish. I give an example that when you have some product, like where you sell, what market you sell, how much money you get in return. The research you as a student or the supervisor have to see matching, where it has good possibility of publication. I see many times I examine so many theses from India and some other country as well. Here I will see that there are very good work, but people end up publishing in poor quality journal. Okay. So, it is very important that we target some high quality journal. So, this is very important. So, here in this basically you can see like say this microgrid, some literature, this paper published in Energy Journal in 2021. So, here architects of this paper, you can see what are the types of problem. Here the abbreviated term you can see here. OP stands for optimization problem, and MOS, what is this MOS? It is multi-objective systems with hybridization of renewable energy resources. So, here your architecture of the power system, you can see that it can be grid connected, or it can be off grid. The next topic we are going to talk, I will again briefly talk about the experience of another researcher. He was from India, so I will share a little bit his experience as well. So, here the architects of the system could be off grid or grid connected. Okay. Then what are the these subcomponents for your microgrid system. Okay. So, here you can see diesel generator, CHP stands for combined heat and power. Okay. Then photovoltaic system, wind turbine generator, electric vehicles, batteries, pumped hydro storage, and this one more THS or something, you can thermal related some system. So, so you can see that when you are doing some research, okay, so story is basically same. Okay, how you show that it is little bit different. So, you consider something additional. So, basically what you consider, what is the methodology, what software you use, like say AI techniques, Homer software, very commonly used in the microgrid. I hope everyone aware of Homer. Okay. Then MATLAB, Simulink, integer programming. So, there are so many techniques. Then at the end, what are the performance indicators? Okay. So, this could be like say optimization cost, okay, cost minimization, emission minimization. So, this way you have the several performance indicators. Okay. Then very interestingly, when we are talking about the reliability, I think everyone have heard the name about the Roy Billington. Anyone heard the name? Reliability. So is the big person in the reliability. So if you say Roy Billington, you Google it, Roy Billington, his name will come. He is big person in the reliability. Okay. So is the anonymous to the reliability. Okay. So basically, when we have this reliability, then there will be several reliability index parameters. Okay. Like for example, average failure rate, how many time system is failing. Okay. Then average outage time, when the failure occurs, as an average, how much duration this failure is there, like 5 minutes, 10 minutes. So what is the average failure rate? This way, then for example, system average interruption frequency, called as the SAFE failure, SAFE. System average interruption index, SAIDI. So this way you will find there are large number of reliability index parameter. How you will judge that the system reliability is high? So there will be some performance index. You will compare, you will analyze the performance index. So this table coming from here, I mentioned yesterday, the review paper written by the same researcher. So in that this reliability index are very nicely documented. Okay, I am not going through each and every aspect. When you have this like this renewable energy, there can be several benefits. It can improve the reliability. Even he used to say that reliability will improve. So then I initially felt little bit confused. I say how the reliability will improve with the renewables. Renewables are highly unreliable, but he will have his own way of nicely documenting. Okay. And he will nicely document, like say environmental benefits. You can say environmental benefits, you can list them: reduction of CO2, reduction of NOx, reduction of SOx, right? So you can GSD reductions, you can list down how you can document. Okay. Then economic benefits. Okay. It could be reduction of COG, cost of energy, reduction in the fuel cost, reduction in the maintenance cost, reduction of the net present cost. So basically you can expand. So here basically in power system, as we know that using the fossil fuel is a problem, causing the environmental issues, and that's why we go for the integration of renewable energy sources with energy storage system in the power system. And this is achieved by analyzing reliability, environmental and economic impacts of the renewable energy sources in the power system. So here the World Bank record on the indicators to measure the reliability and provision of the infrastructure services in some of the countries as presented in the table. So here in this table you can see, get an idea that indicators of the electrical infrastructure reliability. Okay. So, different countries, different region, as an average all countries, East Asia, Eastern Europe. So, different countries you can see electrical outage losses when there is power failure. So, how much is the electrical outage losses? So, you can see this factor in the different region varying significantly. Okay. Number of electrical outage in a month. So, in this also, like you can see, compare for example, in African continent quite high, okay, almost one outage almost every day. Okay. So, if you compare with respect of like say some other countries, it is like say less than one outage in whole month. Okay. So, this way you have the different indicators for the reliability, duration of electrical outage. So, this duration you can see is also significantly varying. So, here overview of the reliability assessment. Reliability is the probability that power system will perform its function adequately without any failure with a stipulated time of the period of time when subject to normal operating condition. When you are operating under normal conditions, you consider any device. Okay. So, it will perform its intended function without any failure for the stipulated period of time under the normal condition. So, reliability is the degree at which performance of the components of the power system result in conveyance of electric power system to the customers with acceptable criteria and the amount of anticipated for intended period. Reliability is the key performance indicator in planning, design and operation of power system. Reliability assessment has become a significant subject due to the sudden increase in the demand of reliable power system at minimal frequency and duration of power outage. So, this reliability in the power system is used by the power utility to measure the performance of the power system. It is used to analyze the impact of the power interruption on the number of customers at load points and the cost that is associated with the power outage. It is used to estimate the substantial impacts of renewable energy sources in the power system. It is utilized by the utilities to determine the balance between the economy and continuity of the power supply. So, here when we are talking about the distribution of the power system, because when we are talking about the generation, talking about the transmission, talking about the distribution. Okay. So, the outage mostly will be in the distribution system. You will not see that much of outage in the generation or that much outage in the transmission. If you see like the outage in the transmission line, so it will affect the significant part of the distribution. So, most of these outage you will see in the distribution. So, here distribution system is technically, as we know, that last segment in delivery of the power system at load points. Stats show that failure in the distribution system is about 80% outage of the total power system. This has demonstrated the need of frequently perform the reliability assessment of the distribution system. Even we have the microgrid which is connected in the distribution system. So, considering its reliability becomes very important. So, here you can see that when we have this like the this transmission or generation, so you will see that outage duration is quite low, but when we have this lower voltage coming to the distribution, these outage durations become significantly higher. Okay. So, most of the outage, significant outages, it will be in the distribution system. Okay. So, here when you want to have some analysis, you want to carry out the study, you will have some network, either some realistic practical network, or you can have some standard IEEE network system. Okay. So, that researcher found this RTBS. RTBS stand for the RBTS. RB stand for Roy Billington, the key person I explained on the Roy Billington. So, system based on his name. So, you have this like the this network, and then of course, you want to integrate the renewable energy sources at the different buses, like you integrated wind system, you integrated PV systems, suitable locations, you have the diesel generators, okay. Then you want to analyze this system, okay. Then of course, you are going to model these microgrid systems. What will be your objective? I am not going into the detail. So, objective could be minimization of the cost of the energy, annual cost. You want to optimize. There can be multiple objective for the cost minimization. Then of course, it will have some constraint that how you know your this power system will operate. Each generation will have its maximum and minimum operation constraints. So, you appropriately model the power system. I am not going into the details of that. I just want to little bit give you an idea. So, here you have a system. Here the system is, you can see, quite large. The load on the system, you can see here something between 15 to 20 megawatt load, and then that load you are going to use through this a PV system, wind turbine, battery storage system, and of course, the diesel generator. So, here in first case, you are mainly using this load requirement through the diesel generator. Then as compared to the first base case, when you are only using the diesel, then you start using these renewables like PV, wind, you try to have the minimum use of the diesel generator. Okay. So, we have to understand, the profile of the PV. So you can see that PV is generating power, say early morning around 6 or 7 to say, depending upon where you are installing the PV system, goes to say 6 p.m. in the evening. So it is generating this power. You can see this power production from PV. Then you have this wind. So how this power production from the wind will be there. Then you have this like the battery storage system, and you will again see the state of charge of the battery, as you are using the battery storage system. So basically, and then of course you have the diesel generator. Okay. So when we have this power production from the photovoltaic, so you can say during the day the diesel generator use becomes minimum. Okay. If you see as compared to previous one, you see that when we are not using the PV or wind or even the storage system, so mostly the load is made mostly by the diesel generator. Okay. So when we are using these renewables, then to meet the load, we are using the renewables to have the minimum use of the diesel generator. But of course, we will have the constraint that battery storage system we will using that it stays between the state of charge minimum and maximum. So all the constraints we have to be considered. PV will be available mostly during the day. Okay. When wind is blowing, we will be able to generate the wind power. But we are optimizing this, so basically it should able to continuously satisfy the load demand. Yeah, so then basically you can have the different scenarios. You can have different scenarios for the different cases I mentioned. You can have only diesel. Then in diesel you add the storage system. You have the different case studies, and then of course you are optimizing the different cost aspects. So you can see these results. I am not going into the detail, but just to present you a little bit idea in the tables. For example, impact of incorporating the wind PV battery system on the annualized cost of the system. Okay, you are considering the different scenarios. Okay, first one is like just you are considering diesel. Okay, so how much is the cost of energy? But when you are incorporating renewables, so the cost of energy is significantly reduced, around 50%. Then impact of incorporating number of wind turbines, PV, battery storage system on the annual emissions and fuel consumption. Okay. So what is the impact on this aspect? You see, in the first case, we were using mostly the diesel generator. So you can see how much is the diesel generator fuel consumption, the fuel like 404, at this figure you can see. Okay. But when we are using the best case with renewables, so it comes down to around 100. So 1/4 diesel is being used. Okay. Then accordingly you will see that when the diesel use is getting just around 25%, then whatever you have the CO2 emission. First case CO2 emission was close to say 1960. Then it comes down to around say 263, 1/3. Okay. So emission reduction is like 1/3. Same way SOx and NOx. So you can clearly see, which is obvious as well, that how much diesel you are using, how much is this cost of that. When you are incorporating renewables, how much renewables you are incorporating, accordingly it will leading to the reduction in the cost. It is leading to the reduction in the fuel, reduction in the emissions. And then talking about the reliability of the power system. Okay. When we have incorporated the renewables, okay, so we may think that system will not be reliable, okay, but we have to judge based on this reliability index parameters. Okay. So there are several reliability index parameters. So several reliability index parameters have been dealt, that this electrical energy not supplied, cost of that, okay, total outage cost, total cost of electrical energy not supplied, emission cost. Okay. So all these different reliability index parameters you are considering. So basically you can see that as we are integrating renewables, the reliability of the system is significantly improved. So here a detailed analysis is carried out. I am not going into too much of detail. Okay. So here this is another example dealing with the this researcher Temitope Adaferete. So is talking about the reliability, economic and environmental analysis of microgrid system in the presence of renewable energy sources. So this paper published in the Applied Energy Journal, which has very high impact factor around 9 I think 10 or I think something like that. And this paper received the highly cited research paper as well. So and here what we are talking, that renewable energy integration in the microgrid, but microgrid not very small in terms of like up to 1 megawatt or half megawatt, but you can see that here research is conducted based on this quite significant size of microgrid. You can see that both small and large systems have been studied. So for this configuration, what it is given in the like again the configuration economic analysis has been carried out. I am not repeating. This case talks about the like the analysis for a large isolated microgrid system. So, this paper, technical, economic and environmental assessment of distribution power system with the application of renewable energy technology, published in the Renewable Energy in 2022. So, here the techno-economical analysis of the renewable energy technology in microgrid system is carried out. Here the wind and solar resources for the location in the northern Cape Town in South Africa province, and the sequential hourly shape of this IEEE reliability test system with the peak load of 40 megawatts. So, you can see that it is quite significant size, whatever you call the microgrid system. Okay. So, is considered. So, here again 5 scenarios are analyzed by using the economic, emission and reliability indicators of power system with incorporation of diesel generator, photovoltaic, wind, energy storage systems. So, again here we consider the network system, and then we incorporate the renewable energy sources of the appropriate location, appropriate sizing. So, here the diesel generator rating 48 megawatt, the PV considering 24 megawatt capacity, wind we considering 24 megawatt, and energy storage system considering 4 megawatt. So, this way we are considering the 5 different cases, and then again we want to you see the objective function. Objective function, it is a objective function. Here it tries to minimize the total outage cost, TOC, total outage cost, minimize the reliability index. This TAC stands for the total annual costs, and EIR is the environmental impact reduction cost. So, here it is considering the reliability aspect, the cost aspect and environmental aspect. So, it is a multi-objective function. Okay. So, here this table provides the data taken from these references. You have diesel generator, wind turbine, photovoltaic, energy storage system, inverters. How much are the cost? So, diesel generator says $2,700 per kilowatt. This is the initial cost. Maintenance cost is $0.01258 per unit of electricity. The lifetime of diesel generator 25,000 hours. Some other factors are provided. Wind turbine, initial cost $3,500 per kilowatt. Maintenance cost $20 per kilowatt per year. The lifetime is 25 years for the wind and PV system. So, this way all parameters are provided. Then you are analyzing the system. Total cost of the system you can see here in this graph. We consider the different scenarios, like say first only like the diesel, then we kept on adding the renewables, PV wind energy storage system in sequence. So, here you can see that this cost here in this last scenario obviously coming down, and here in this table you can also see these different cost aspects. Costs are reducing, cost saving is there, which is presented in the detail in the table. Then you can see the effect on the emission for these different scenarios, that CO2 emission, as you see for first case 1920, here it comes like 538, so just like 1/4. Same way this SO2 and NOx emission reduction is there. You can also see that about the fuel consumption, what you had in scenario 1. So, first like the first 4 figures you see coming closer to 10,000. Here if you see in the last case, first 4 figures less than 2,500. So, fuel used is just like 1/4. So, you can see that you are using in first case this much of fuel, then how much fuel you have here. So, 70%, approximately 70% fuel saving is there. So, you can see 75% fuel saving is there. Talking about the reliability index parameters. So, you can see how many these reliability parameters are considered. So, all these you can see reliability parameters considered here, SAFI, SAIDI, KAIDI, so etc. So, you can see that I am not going into the detail because of the time constraint, but you can see that with the integration of renewables, reliability is also significantly improved. And with you can see how the system is operated, maintained very well. Okay. So, here this student, I am sharing his presentation, this is the author in all the first paper. So, he did PhD with me. So, if you see from the down, first paper he wrote like the review paper that I showed you, the review of the distributed generation. Then you have the paper in applied energy, reliability assessment of distribution system with renewable energy integration applied energy. Then another paper, reliability and economic aspects of microgrid system with integration of renewables. Then you can say reliability, economic and environmental analysis. Okay. What you consider something additional, your rewrite is almost complete. You do the fresh writing. Then you can say optimal energy management for PV, wind, battery storage system, microgrid system, technical, economic and environment assessment of the distribution power system with renewable energy technologies. This paper talks about the optimal energy management and technical, economic, social, political. See how many factors are being considered. Technical, economical, social, political and economical benefits analysis of grid connected PV, wind, fuel cell, hybrid energy systems. And then very recent this one, design and techno-economic assessment of standalone PV DG battery storage system for electrification of rural areas. So, I briefly presented the research work from this student. So, I just will conclude this presentation, but some papers I will try to share, and if anyone needs more paper, I will be happy to share. So, I will just for this presentation I will stop here, but I will be happy to provide any questions you have, maybe technical, economical, general. Okay. So, you are more than welcome to ask. As you will see that my job only is to encourage publication in high quality journals. Okay. So, this is very important, you know. So, even you can search for this person Google Scholar. If you will find where my name is not there, so quality of journal will generally be reduced significantly. Okay, you can search is now itself, Google Scholar page. So please ask few questions. Any question, please, from online participants? How many are online participants? Yeah, please, welcome. Please tell your name and where you are working, student, faculty. Introduce yourself.
Hello.
Yes, please.
Hello.
Yes, please.
Sir, Manbir from Thapar Institute, Patiala. I'm Manbir from Thapar Institute of Engineering and Technology, Patiala, Punjab.
Yes, excellent.
Sir, I have one small question, sir. When we are considering the reliability tax with respect to the multiple sources involved in the system, then are we assuming, because the renewable energy sources are not certain in nature, so are we considering that these sources are available before taking out the generation adequacy?
Yeah, so you know that initially as explained, like how different reliability index parameters are defined in the literature. For example,
yes. Actually, this topic seems to be very interesting to me. I would like to see your paper as well.
Yes, most pleasure. You can just message, email me. I will be happy to provide the papers. So, but you can see that how this reliability, different reliability index parameters are defined when we have this microgrid system with the integration of different sources. So, system becomes more reliable. The failure of microgrid as such will be less because there will be if the system are in parallel, you are adding the generators in parallel. If you have the system in parallel, it will increase the reliability. Of course, if you are adding the component in series, it will decrease the reliability. Okay. So all these, yes.
But for renewable energy sources which are uncertain nature, so we are assuming that these units are available to share the load demand.
Yeah, so basically, as you will see that very interesting point you asked, that we for example how we are meeting the load. Okay, so you can see that photovoltaic generally will be available during the daytime, and as the sunshine keeps on changing, accordingly you can see the power contribution from the photovoltaic system accordingly. Then
okay, so based on the time interval in a given time interval, we are considering the units and we are carrying out the generation adequacy performance.
Yes, yes. So here also, like you can see, same way, what is the wind profile, accordingly how much the power is being contributed by the wind turbines. So all these things, like based on the availability of the data, availability of the information, and we are trying to optimize our program, meet the generation with the demand. Okay. So we ensure that the system frequency is maintained, and that's something with the certainty, like how much we are providing through the battery storage system within the limits of the SOC. So we are doing that. And if there is like say less power from the renewables, that we are meeting either from the batteries or from the diesel generator.
So this sampling time we have taken, I have not seen that because axis is not visible. Sampling time. Hours.
Yeah, so maybe this all in different papers, the studies are quite detailed one. So I have just presented very briefly. If I present this whole, it can take 5 days just talking on the reliability.
I am student of Professor J.S. Dillo.
J.S. Dillo, yes, I heard from the J.S. Dillo again, the student of Professor D.P. Kothari.
Yes. So,
I am also the student of Professor D.P. Kothari.
D.P. Kothari and J.S. Dillo are my supervisors for PhD.
Okay.
And D.P. Kothari recommended your name for as one of my student examiners, but your name was not taken. Yes. Unfortunately, your name was not.
No problem. Like you see, yesterday we talked regarding the collaborative. The point one we mentioned, it is not always that you will have MOU, but there could be when you have some link, some collaboration, you can have several. For example, anyone consider potential examiner, for example, or for example you want to have some conference, for example US or some other location, you explore maybe some possibility how it will be presented. So there are different possibilities when you have some networking, it is really very helpful.
Yes, such type of GIAN courses are helpful for social networking as well.
Social, and then of course technical knowledge, condensed knowledge.
Technical knowledge is always there, but social networking as well.
Yes. So like in 5 days you can have significant condensed knowledge, resources, and which depending upon your research interest you can further build up.
Find the direction. Yes, help us to find the direction.
Yes.
Thank you so much.
Thank you much. Please, anyone more? Any questions, please? Anyone from the physical mode? Any question, please? All right, so if no question, maybe we will have the short break, maybe just short break, maybe 5-10 minutes, and then we will start the other presentation. Thank you all. So we will meet in maybe 10 minutes time again. नेक्स्ट और लगा देना 5-10 मिनट में उसको भी शुरू करेंगे, थोड़ी जल्दी कर देंगे उसको भी।
सेटअप कर देते हैं।
कर दीजिए बिल्कुल। ये थोड़ा टॉपिक थोड़ा फास्ट करने थे तो मैंने कर दिया।
This one is
खोलेगा तो पता लग जाएगा। नहीं ये नहीं
ये नहीं
है, एक नहीं ये नहीं, वो लास्ट नंबर होगा, देखिए 17 18 ये भी नहीं है, 3। ओहो ये मैंने अभी दे ही नहीं लगता अभी आपको, मैं एक मिनट अभी आपको शेयर करता हूँ।
चलो
नहीं यहाँ भी नहीं, मैं अभी शेयर करता हूँ मेरे लैपटॉप में।
अभी आप लैपटॉप मोबाइल में है सर?
नहीं लैपटॉप से शेयर कर दूँगा।
सर पहले चाय पी लेते हैं उसके बाद
साथ साथ बैठ कर दूँगा।
सर आ गए।
कोई बात नहीं, अभी मैं चाय Okay, good afternoon. So, we are going to start lectures 17 and 18, microgrid control in islanded mode of operation and grid connected system interfacing with the utility. Okay. So, this will be again like the short presentation. I just want to discuss like one of the paper very briefly with of one of my PhD student which I supervise at University of Pretoria, Ramesh C. So, he in India initially worked at DIT Dehradun. Most of you would have heard the Dehradun. So, when I sometime visited there in his college, then somehow he interacted me, then he said he want to do PhD, he expressed interest. I say we can explore maybe, but like if you are very keen, you can explore maybe with some advanced countries like USA, UK. And then he said, no sir, I have to do PhD and do only with you. So I said I have nothing special, but said no sir, if I will do PhD, I will do with you. And he asked me several times. Okay, then say if you are very strong determined, then there is no question of USA, UK, you know, when you are really something strong determined, whatever region, you have your preference, whatever way you see. So, he did, and then I told that okay, like we have to see, you know, something realistic condition. I don't tell unnecessarily, you know, we have this. I try to tell little bit things more realistically. Okay. So, I said that okay, that like at that university we may not have something like this, something great funding facility. Okay, I try to explain him the realistic situation. Then I said that okay, you explore some, you know, scholarship possibility. Then he applied maybe for some you know, this international funding, and luckily he was very successful. So, some European, maybe I don't know what exactly name is there, but that's very competitive, and luckily he was successful. So, the financial issue was not a problem. Okay. So, he had the scholarship. So, you will see that another great point I want to share briefly. He did the great part that from his side, that he did his PhD very much timely. Okay. What is, you will say, nominal time, before than nominal time. Okay, I will not tell exactly how much, but if you ask me confidently sometime, I can share with you. So, what I am trying to say that he completed his PhD in the nominal before the nominal duration of time, and I will show this last slide is, you know, presentation, you know, publication record was also, you will say, excellent. Okay. So, basically if you see that there is you know, we need not to be like say everyone like the extraordinary, you know, but someone is like say little bit more deterministic, you get little bit proper mentoring, advising, one can do with God grace things quite nicely. So, here basically one of the paper I am briefly discussing. So, to try to match you know what is you know the title of this presentation, that this microgrid control in the islanded and grid connected mode of operation. So, this paper basically talks about the multi-objective optimization of hybrid renewable energy systems using the reformed electrical system, cascade analysis for islanding and grid connected mode of operation. So, it was published in IEEE Access. Previously IEEE Access appeared to be okay, now it is decreasing, to be little bit honest. So, of course, it is open access, paid journal, I do not encourage much, but sometime like when we are in the member in the team, so decision is not taken by one person, okay, and I do not try to dictate the decision. I will have just my advisory role. I do not tell like that we have to only do this way. Okay, I will have just my general advice, and then maybe as commonly agree, we try to do that. So, here this paper presents a methodology of the reformed electrical system cascade analysis, abbreviated as RESCA, for the optimization, try to optimize design, optimize the system, optimization of hybrid renewable energy system comprising of the wind, photovoltaic, battery storage systems, non-intermittent load, and the grid as the system components, and it considers 4 different configurations in islanding and grid connected modes for the analysis. So, 4 configurations of hybrid energy system is optimized using this technique RESCA with constraints such as final excess energy, renewable energy fractions like this sum of the index, energy generation ratio, loss of power supply probability, and annual system cost. Okay. So, 4 different configurations are considered, and the optimization is realized for a residential load in the Newark. So, it is not New York, but is Newark, okay, USA, consisting of 100 households with a daily consumption of 3 kilowatt hour for each house. Okay. So, the paper presents the application of RESCA methodology for optimization of hybrid renewable energy based on reliability and economic constraint for both isolated and grid connected mode of application. I will present this very shortly because after this we have one more presentation remaining. So, I do not want to go in fact even too much detail of this paper. Can you think that how much this paper length will be there in IEEE format, IEEE Access? Any idea that how many number of pages this paper could be there? Number of pages? Generally, like if you IEEE paper, okay, if it is normally transaction, previously it used to be 8 pages limit, then 10, it could be 12. So, this paper 23 pages. So, very long. So, I just want to briefly discuss. Even I like more telling some stories of these, some successful or some students to motivate more. So, here basically it considers the 4 different architectures of the systems comprising, you can see here 4 different these cases are considered, like the PV systems, battery storage systems, wind systems, dummy load. The first these configurations. Second you can see that these configurations. Here you see that grid converter connected with the utility grid. Then in the configuration C, you can see that here battery storage system is not there, and you can see is on this like the here. So this way you will see that 4 different configurations considered here, and here the optimization constants, what these are considered. So explained in this table, and you can see that system components and the application constraint for various system configurations, what we 4 configuration we consider. First one like PV, wind, battery storage system. In second PV, wind, battery plus grid connected system. Third one PV, wind, and like that, and then fourth one with grid connected. So, and these different constraints are considered. So here basically in this area you can see quite detailed literature review analysis. So summary of the studies conducted for hybrid energy systems optimization. What are the different optimization techniques which have been used in the various research papers? What are the different system components have been considered? Whether the system is off grid or on grid. Okay. So you can see off grid, mostly off grid, here off or on grid, off and on grid. So except 2 mostly are the off grid. Then optimization constraints, and it lists down some of the important findings. Okay. So as I mentioned, I will be just want to quickly complete this, and then we have this next presentation, remaining one. So here then we have the technical input, technical parameters, technical and cost data required for the system modeling, and the references are provided here. So this technical information includes for this PV module data. So you'll see that PV several information for the PV panels. Same way you have the wind energy conversion system, so you can find all the required parameters. Battery and energy storage system, manufacturer and all these battery systems required parameters, converter data, and the this NIS and grid data. So all these technical and cost data which have been used, and this table shows the details of hybrid renewable energy systems with the different optimization constraint for the configuration 1. So which are provided here. I am not going into too much of explanation. I will be happy to provide these papers. Then you can see for the same way configuration 2, configuration 3, and then basically you can compare the details for the configuration 3, and then basically you can compare these various optimization techniques, compare the optimization techniques with respect of this particular technique used in these papers. Okay. So, with respect of these other topics, other optimization techniques, what are the issues with respect of the other techniques. Because of time constraint, I am not reading through or going through the detail. Then it basically suggests you the possible improvements using these particular techniques. Okay. So, here basically just to very briefly list down this key observation, that this technique has overcome the drawbacks of the primary methodologies by incorporating multi-constraint optimization criteria for both on and off grid modes of operation. And this has included variations in the PV and wind energy conversion system performance based on the temperature and system modeling. So, it is a very detailed paper written. So, you can see that this student did his PhD on the topic multi-criterion optimization of isolated and grid connected hybrid renewable energy systems using this technique in reformed electric system cascade analysis, University of Pretoria under my supervision. So, you can see that he published for high quality journal papers, or like say IET RPG, industrial electronics, IEEE electric power systems research. In addition, he published conference paper, book chapters, etc. But he did his PhD quite successfully within the normal period of time. Okay, because of the time constraint, I do not want to go in too much of detail. As we said, we are happy to provide the additional resources, research papers, but I will be happy to respond some of the questions. So, please, if you have any questions, technical, economical, environmental, any kind of question you have, you are more than welcome to ask me, online participants and physical participants. So, please, if you have any questions, expect at least 1 or 2 questions, maybe 1 at least from the online, 1 from physical. Okay. So, we will not end up before we have 2 questions. Right. So, please ask at least 1 question, physical 1 question. Maybe anyone from the physical, please, any question, general, any question? Not technical, anything you want to chat with me, if you have any queries. Your voice will also be recorded in the GIAN program. The photos also come for the participants if they ask question? No? So, make the provision.
It is there in MS Team. If somebody asks and somebody
Yes,
turns on the camera.
yes, it can, yeah. So, please, if you have any questions, fine, otherwise we just will. Anyone raising hand? No? Okay. Yes, please. Yes, please. Please tell your name, your affiliation.
My name is Dr. P.K. Bhatt, sir, Weltech University in the Chennai.
Chennai, excellent.
Sir, actually, I want to know about the last 2 days you are given presentation, sir. Actually, sir, any experimental setup, sir, you have, sir? Can you show me? It is, I think it is better because totally last 2 days you are given presentation is very nice presentations, no doubt. But any experimental setup, sir, you done anything, sir? Can you show me it is a better understanding about the microgrids regarding what you are already presenting last 2 days? Any one experimental setup, sir, you have, then can you give, sir, that is it is better get knowledge from about what you presenting. You have any experimental setup?
Yeah, so in fact this is really very good question about the the experimental setup. As you see that the microgrid, okay, microgrid what we are mostly talking, okay, and generally I am presenting the situations like 5 or 7 years earlier when the student did their PhD or say 7 or 8 years earlier at University of Pretoria. So at that time there we were not having any such sort of microgrid facilities, and sometime you will see that like when you want to consider the different varieties of systems, like one of the studies shown for really big systems like 40 megawatt. So depends upon if there is any availability, but we used to have there at University of Pretoria, there we have another scientific laboratory, CSIR. So they also conduct the research. They have also got some research laboratories, research facilities. So on some of the project we jointly work with. Okay. So I think one of the student did some study related to that, but in some of the situation like it may not be feasible or possible to have this realistic hardware microgrid setup. Okay. And so even whatever here at University of Sharjah we have got some facility, some research facility, particularly talking about these small size photovoltaic systems, not very big, 3 kilowatt, but it has the tracking system, it has features like this bifacial PV panels, it can be connected with the grid, it can be isolated. So some research we have done, but with these students, so this was mainly the like simulation study. As I explained, that simulation study is equally important in the power system. So that's the case. So I hope you got my answer, please.
Yes, sir, I got this answer, but you have done the simulation work, I think.
Yes, so yeah, even please you are welcome to interact me at later stage as well. So I can see, I can connect you, I can direct you probably some more information at later stage as well, additional information.
Okay, sir. Thank you, sir.
I will be happy to discuss. Please you can contact me through email or WhatsApp, and we can try to provide you some additional information as well. Some more questions, maybe anyone from online or physical, please.
Sir, namaskar. Namaste, sir.
Namaskar.
Sir, I am Dr. Kumar. I am basically from Odisha, but working here in Hyderabad, and I am a professor in the Department of Electrical and Electronics Engineering at Srinidhi Institute of Science and Technology, Hyderabad.
Very nice.
Actually, I am hearing since last 2 days, so your lectures, it is good for us also to see hybrid microgrid system. And different papers, I think you have reviewed many papers, and also today whatever you said about reliability indexes, these are the things we discussed, and you discussed it nicely. So my question not related to these things, whatever the technical aspect of what you discussed. So only one non-technical question, if you permit me, then I can.
Sure, please.
So nowadays in India, what exactly the scenario is? So the demand of core branches are not there. Whatever we expected, the core demand, Windows, smart grid, microgrid, and many new technologies are coming up. But day by day, what we are observing, students are not showing interest towards take admission in the core branches. So that is the reason, because I am working here, last 1 year, we are not getting MTech students. When I joined here in 2017, full MTech students in our branches of power engineering. So last 6 years, students were there. But in the consecutive last years, no students. So as a result, many students are moving towards these computer science branches like that. So exactly what happening there, sir? Is it the thing going on there, or why these things are happening? What is the demand for the electrical engineers in future also? So because people are talking about PV. Many plants are coming like that, but what is the job opportunity, what is the scope, where the faculties, actually this is the practical things happening, excluding the NITs, IITs, those who are working in private sector also, so they are facing a lot of problems. So what exactly they are going on in your areas? So what exactly we can do, sir? What exactly this PhD, everything we can take the qualification, students will do the research, where they will go, where is the job opportunity?
Yeah, so thank you very much for this very interesting questions. In fact, the very important problem you have raised. Okay, particularly this trend, we see that trend. The trend you mentioned about the PhD student dropping for the admission, master students dropping the admissions, mostly undergraduate students going in the computer discipline. Okay, so this trend is not in India, but this trend is global. Okay, and you will see the situation particularly. Just COVID, so which was the major transient, okay, sudden disturbance, and still the things have not been fully improved. Okay, there has been improved, but you cannot say that the situation which was before COVID, it used to be there, that it is still fully recovered. Okay, so but some of the things you mentioned, and you will see that electrical engineering, for example, one of the very core branches, but you will see that globally, that whatever our electrical engineering used to be there, conventional electrical engineering, so there the curriculum, everything is getting too much dynamic, even the contents by default, practical aspects are changing. Okay, 30 years, 20-30 years earlier, we just used to talk simply generation, transmission, distribution. BTech, there could be 30 or 40 courses, 70-80% will be just core courses. But now you will see how the trend, it has changed that in 4-year degree bachelor, some university first year common, some university even 2 years common, 4th year final project. So only 1 year student will studying core courses. So this trend is like say almost everywhere, and now the approach is getting more towards the little bit more disciplinary approach. Even for example, the faculty, if we just are very traditional, just only teaching only the, for example, conventional courses, okay, for example, machine or power system, even some universities, particularly private sector, the admission has significantly dropped. That is the realistic situation. So unless the faculties are not very dynamic, so it is really a big challenge. Even I recall I have contact with so many faculty members in India, even more than you people be having. Okay. So even when people will ask me, can you please suggest the examiners' names from overseas, they will ask, can you suggest the examiners from India as well? I will say, India, you can search it. They will say that no, but you will tell us better. Okay. So the point what I am trying to say, I have one faculty, Professor Manohar Mishra, he is in the electrical department, but he is more specialized in the computer science discipline. So we really need to have, as technology is changing, so we cannot just only dependent upon the conventional topics, whatever the new techniques are coming. So we are equally using, whether it is electrical engineering, like AI based course we teach in the electrical department, same thing it will be taught in the computer science discipline, whatever the programming, machine learning, whatever they are using, we are also equally using. If
so, that means what?
Yeah, we have to. The point what I am trying to mention is that we have to be more dynamic. We have to expand that. Even computer science is not something unique or something specialized. We are also quite expert, and we can adapt to that expertise without much difficulty. Even part of the course, we have the capability to deliver. If there are more students coming, so we can say that electrical department can also offer the courses, can contribute in the joint this research activities. Now things are getting interdisciplinary. So things are totally changing. I gave you an example, for example, NTPC, for example, which has business in the area of coal and gas. After 5 years rule comes that there will be no new plant for the coal base. So their business they know that their business is going to be closed down. So if they don't update depending upon the situation, if they are not dynamic, things are going to be slow down or die out. So we have to see how the trend is there. So we have to tune and update to that accordingly, and we have to have very positive attitude. We understand sometime things slow down. We have to be little bit peaceful, but at the same time we explore all the opportunity with patience, and I hope that we can survive and we can do quite well. So I hope you got my response.
Yes, your very good response. Your response highly appreciated, sir. But thing is that we have to update ourselves. We have also designed the syllabus, keeping all these things in mind. And in electrical core also only 4 to 5, 6 subjects we are giving to the students, and the rest of the subjects we are taking from the computer science.
Yes.
That elective here we are giving also for the BTech students.
Even
But we are not getting MTech students here. That is the issue. So that is the reason somehow in the research area we are lacking in the research area. because we are not getting students actually. MTech and PhD we forget, but in private we are not getting also MTech students. But anyhow, what we said is we have to go by the situation, we have to keep patience till that time will come. Very good, sir. I appreciated what you said. But what about that in your university, only this 4-branch electrical or any
No.
related branch?
Even I wanted to add, for example, in our department recently they opened the program in the biomedical engineering. Okay.
Yes.
It's not only the electrical department, but electrical department is a leading department along with this medical institutes. So program in the biomedical engineering. So we have to be really dynamic. We have to expand our possibilities. Even for example, one of the department in engineering what we have at the University of Sharjah, there is a full department on SREE, Sustainable and Renewable Energy Engineering. So there is a full bachelor program on this sustainable and renewable energy engineering. So we have to see how the trend is there, and accordingly we have to update our syllabus, update our activities. The research again you mentioned. So in that situation, networking, collaboration is extremely important. Even if there are provision, you can explore maybe some remote supervision with some universities. If you have some good networking, you can come out with some joint publication, and you can have some good research output. Like I want to give you an example. For example, like say now you will see that Uber or Ola, how many car they own? I think no car at all, right?
Yes.
Almost,
Yes,
eh?
yes.
But still they are providing excellent service. Okay, so
Yes.
in some situation like we may not have the student, but if you are very dynamic, you explore, you try to have network, you have capability, you contact, and if where there is provision, you can do some remote supervision. You can still contribute, still publish, keep your profile updated. I'm just telling based on my experience. Like even I tell honestly, University of Sharjah, there is not like something very great research opportunity facilities, but I have still very healthy and very active contacts with my previous university. I keep on getting few students from there. So this way, like you have to be very dynamic, very positive, try to show your potential, that you can do really very well, and you can deliver so that you don't run behind the student, but student are behind you, and you can be more in the selecting mode.
Yes, yes. Yeah, nice.
So that's the positive way I try to encourage that there are always challenges and difficult situations, and
Yes.
that's why all this optimization and everything comes when we have this resource constraint, difficult situation, then we try your best. So this is really great point that you raised, and in the yesterday's meeting we talked that one of the great aspect is that through the GIAN program, that networking, collaboration, people talk about the MOU. MOU is like a kind of one documentation, but more important, at the end human being will work. Okay, if you have some networking, collaboration, if MOU is there is good, but at the end individual context, how things at the end in progress. For example, if I know the director of any institute, it doesn't progress too much, because the director in 2 years may get replaced or changed. If you have some good contact in the faculty member in the electrical department, maybe that contact will live for 10 years or more. So, the contact, proper contacts, networking, research contribution, research output, extremely important. So, networking, contacts, collaboration, long term contacts, collaboration, this is very much essential. And then some points you mentioned, when you are good networking, sometime you want to publish or present paper in this conference overseas. Sometime you may not in position to travel because of several reasons, maybe sometime suddenly visa issue or like that. So, if there is some networking, some collaboration, you can find some solution for different aspects.
Yes. Thank you, sir.
Any more questions, please, from anyone, please?
Thank you, sir.
Thank you very much. Online, physical, if you have any more question. If not, then we will end this session, and then we will have just few minutes break, and then we will continue with the last presentation for today.
वन बोर्ड मैंने देना है सर।
नहीं, ये PPT है। So,
Full-time research scholar at the Department of Electrical Engineering, IIT Bombay. From 2017 to 2019, he has served as R&D engineer in HVDC grid system at ABB Global Industry Service Limited, India. In July 2019, he joined as an assistant professor in the Department of Electrical Engineering, MNIT Allahabad. Dr. Sarkar joined the Department of Electrical Engineering of NIT Rourkela in March 2020, where he is currently serving as assistant professor. Thank you so much. It's over to you.
okay, thank you. So, I am audible, right? Okay. So, let us start the last session of session of today's session. So, today in this session we are going to discuss about fuel cell. So, it will be introduction to fuel cell, but before we start with this, let me, so this is what that I am going to present today. So, electrical power source, why fuel cell, and different aspects of fuel cell. But before I start, let me ask you the very big question, that is why electrical power and why we are using electrical appliances equipment. So, anybody can answer this? Why? First question is why electrical power,
Why? There are so many powers are available, right? So, power means you can drive using, let us say, diesel engine you can drive, let us say car, forget about anything else, let us car. So, we can drive car using IC engine, you can drive car using electrical motor. Why we prefer for electrical thing? What is the answer to this? You people are from electrical background. So, if I ask, or if somebody asks you, let us say any random person asks you this question, that why electrical power, why we are prefer this, what would be your answer? So, anybody can answer?
Sir, it is easily convertible to other energy rather than
Let us say for car, IC engine based cars are very much suitable and it's a state of art, right? But still we are moving towards EVs, right? This is one. So, it is not like that it is easily, means for a specific application we can use it. Okay. So, any other reason? Huh? Pollution, when you are generating electrical power, somebody is generating somewhere, right? So, you are using this AC, so somewhere coal is burnt and power is generated. Okay. So, pollution is there, not here, but pollution is definitely there. What else? What is the major reason? Do you know diesel locomotives that we have in India, because I have seen in India, those are actually electrical in nature. Do you know that? The diesel engine runs an electrical generator, and that generator produces electrical power and it runs electrical motor, and that electric motor runs the train. Okay. So, if you can, so that is the first question that I want to ask you. I remember last year I saw one video, I do not remember whether it was on YouTube or whether it was on WhatsApp. I saw one video where a person wakes up early in the morning. Okay. Now, every equipment or appliance that he is using at home is powered by not electrical, powered by some, let us say, some fuel which is emitting some gas. Okay. So, he is using trimmer, that is some diesel powered trimmer, it is emitting gas. He is using toothbrush, electrical toothbrushes are there, right. So, using that diesel or petrol powered toothbrush, okay, those kind of thing. Oven is there, there is a chimney from where the exhaust is coming out. So, every equipment is not electrical, but so that is also feasible, right. If we think about, let us say that emission, let us say forget about emission, but it is feasible, right. But still we are preferring electrical power. What is the reason for that? That I want to know. Transferable to long distance, okay, that is one. But now we are not relying on conventional power generation. We are relying now on distributed power generation. So, that also out. So, anyone from online participants, anybody can answer me this, why electrical power? Why electrical power? What is the meaning?
We can easily control the electrical parameters compared to other form of energy.
That is a very good point. That is a electrical, the controllability of electrical parameters are much more what I should say, you have more degree of freedom than the mechanical thing. That is one point. That is correct. Another thing.
The response is very quick.
Response, if it is a mechanical system, electrical system cannot make your system quick. Let us say you want your car to be accelerated in 10 seconds. If it is a IC engine based vehicle and it is electric engine based vehicle, both will give you 10 seconds. Okay. So, electrical responses are faster, but not mechanical, ultimately using for mechanical thing. Okay. So, you relying on mechanical. Okay. Electrical system efficiency are much more than mechanical system efficiency. That is one of the major reason. Okay. Another reason that this is the most important reason, because what we are doing now, we are trying to harvesting what? Renewable energy, right. So, now renewable energy you are converting, so you are generating power. So, that power is electrical power which can be easily stored. You can easily store in the form of what? In the form of, let us say, battery energy storage, you have this inductor, superconducting inductors, there you can store the electrical energy. So, storing of electrical energy, the efficiency of electrical energy is superior, control of electrical energy is superior. These are the major reason because of which we are using electrical power and we are looking for electrical power, right. Now, next question is, what would be the, so now you need electrical power, right. So, you are looking for what? You are looking for electrical source, electrical power source. Okay. Now, we as an electrical engineer, if some random person comes and give us a power source, let us have it and you power up your home, let us say, forget about industry and other thing. Let us say that person is giving you an electrical source for your home. So, what are the things that we will look into, that whether it is suitable for you or not, how will you judge, what are the parameters that we will look into? Why I am asking these questions? Because conventional power system was there, now we are coming up with PV, wind, fuel cell, battery, there are geothermal, some micro hydro, mini hydro power plants are there. How to choose which power source will be suitable for which application? Because why I am asking this question, because it's not academic research. Whatever you do in academics is for you do the research, because you cannot do something immediately on the practical field. You have to do some research, you get some knowledge and then you can implement it for the industry. So, let us say if a power source is given to you, if it is not practical, then it is not acceptable. So, if some power source is given to you, how will you understand whether that power source is acceptable or not? So, what are the parameters that we will look into? What parameters? Anything you can answer. Let us say, what will you look into? Why the power source should have what?
Sir, nature of the source.
Nature of the source in the sense DC or AC?
Yes.
Okay, DC AC, okay, very good, one point, DC AC, that is one of the point. What else?
Output power, voltage and current.
Voltage level, current level, very good, yes.
Power density.
Power density means how much size and this volume, correct, absolutely correct. What else? Capacity, yes. Power rating, yes. What else it could be?
Whether it is environmental friendly or
yes, very good, yes, correct, that is also a point, whether emissions are limited or not, whether that emissions are acceptable to our environment or not, that is correct. Major points are coming up. Okay. What else? Why? Because we are going to talk about one power source. So, let us see.
Also see whether it is supplying continuously or it is an intermittent source.
Absolutely, very good point, correct. Protection schemes, okay, protection schemes, right, that also will come, yes. Anyone from online participants?
Electrical source is not available as such. What type of energy we have to use to convert into electrical energy, that is also very important to make electrical power source.
Okay. So let us say my point was, let us say somebody is giving you the power source, whatever be the input, the output of the source is electrical. So, if that kind of source you have, so what could be the parameters that you will look into?
So, can it be cost and reliability of the supply?
Absolutely, absolutely correct. Cost and reliability, absolutely. Yes. So, most of the points are covered. Okay. So, first thing that we should look into is the availability of that power. Let us say if it is a solar powered, if it is a solar power, at night you do not have power, right. So, first thing you need power 24/7. So, if it is solar power, let us say the person is giving you, let us say solar, which is relying on sun, then you cannot accept that power. So, you must have a battery battery backup with that, then only it is acceptable. Then is reliability. You bought it, you got it, you used for let us say 30 days and then it has damage, it is damaged. So that reliability is not there, so you cannot use that power as well. As you mentioned, size and weight, definitely if for your home he is giving he or she is giving you a power source which is a size of your home, then you cannot accept. A generator, diesel generator size is there, and if you are going to take it, you cannot accept that. Definitely cost, definitely cost. What are the three things that you need to look into? First is the installation cost, then second is the running cost, and third is the maintenance cost. All this cost matters a lot. Infrastructure cost like solar, wind, if you are going to see, infrastructure cost is more, maybe running cost is very low, but maintenance cost might be there. Let us say battery, the maintenance cost is high. Okay. Now emissions, as you mentioned, emissions, solar no emission, wind no emission, but there are diesel and other power plants which are having emissions. Now intermittency, if it is intermittency means let us say solar, wind and all, those are what? Those are weather dependent. Okay, it's we did experiment on solar for charging battery. I should not say EV battery, but we started with battery, and it was the solar panels were put on the direct sunlight, and it was varying like anything. Okay, so that is intermittence in nature. Durability, it has to withstand harsh weather condition. It might happen that you are putting this in a very, like one professor was mentioning that they have installed lots of solar, they installed a solar park, and they installed this PMSG, permanent magnet synchronous generator, where the generator magnets were deteriorated because of extreme humid condition. So magnets, he was mentioning that magnets becoming powder. Okay, so that means it is not having that durability, right? Durability under extreme condition, durability over the years. Now let us say a battery, if you have a battery at your home, what happens over the year means battery, now most of the home equipped with inverters. So if you have an inverter at your home, inverter comes with battery. So when it comes to battery degrades, battery life degrades with time, state of health of a battery degrades. Okay, so those things that you need to look into. Now output, AC and DC. So you have to look into whether it is AC or DC output, and accordingly you have to make arrangements. Now whether it is a voltage source or whether it is a current source, that is also important. As you mentioned, protection will depend on, if it is a current source, you do not need any short circuit protection, or you need, it should not be, if it is a voltage source, short circuit protection should be there, open circuit will not be a problem. If it is a current source, the open circuit will be a problem, short circuit will not be a problem, right. So these are the things that you need to look into whenever you get a power from something, and then immediately you will think that okay, this is acceptable and we can use it. It is not like that. Okay. Also I mentioned cost. So sometime the power sources which are feasible in nature, and but because of cost we are not using. Now fuel cell. So hydrogen fuel cell, what it happens, there is a chemical reaction happens, and because of that there is a electrical energy, and there will be water and heat will be generated. It is abundant availability. Sometimes people say that it is renewable energy. It is not renewable energy, because it is H2 is availability is abundant. So that is why we do not think of that. It is like free energy. Now emission is almost zero. Okay, emission is almost zero and nearly zero carbon emission, and it is efficient. I should not say it is efficient. If I tell you that what is the efficiency of a power plant, if anybody can tell me the figure, 40%. It is very low. It is also around 40 to 50%. It is not highly efficient, but yes, efficiency is of the order of this, because there is a heat is also generating. Okay. Now sometime we say that what is the emission of electric vehicle? What is the emission of electric vehicle? But Emission of electric vehicle? Emission of electric vehicle is not 0. Okay, you cannot say. If you go and see the data sheet or a specification of any electric vehicle, you will see that it is not 0, but it is dependent on what is the emission that is generated by the power plant. So, what is the application? So, now it is, you can see it is, I remember if I see here bus, I remember this bus. I remember long back in 2013, 2000, I think 15. In 2015, I was in the morning walk. Generally, I go outside, and this is NIT Rourkela campus. I was in my PhD institute. I went outside for a walk, morning walk. I saw a very big bus. Okay, very big bus, and that bus was a fuel cell bus. Okay, it was in 2014. And that bus was by some very renowned company from India. Okay, so you think that bus is that bus in 2015, either 15 or 16, I don't exactly remember the year. So if the bus is in 2016, maybe they started work 5 years back. So if I assume 5 years, so it is 2010. Okay, so there are industry who started working maybe 20 years back on this fuel cell and fuel cell vehicle. Even fuel cell vehicles are available. There are companies which are already launched fuel cell hybrid vehicles. Okay, so there are applications like transportation, fuel cell train, hydrogen train. Very soon India is going to test hydrogen trains. Cars are available, trucks are available, utility power supply. So there are fuel cell. We'll see the power rating of the fuel cell. There are fuel cell which are sufficient enough power generation which you can supply to the utility or connected to the grid as well. Okay, microgrid power supply. Here also you can fuel cell based microgrid you can think of as a distributed generation. Power supplies to residential commercial building, and also as an energy storage for off grid solutions. That I will talk about. Just one line I will tell you, understand why we are saying it is energy storage. Okay. And what is the difference between battery and fuel cell? If I say both are black box, so if I say if you want to compare with fuel cell and battery, the first thing that you can see into, fuel cell needs continuous power flow, and so it does not need any recharging or charging. Charging is not needed. So actually it is similar. What happens in battery, you charge the battery, it stores the energy, then delivers. Here in fuel cell, what happens? Continuously there is a flow of fuel, and it is continuously chemical reaction is going on, and continuously power generation is there. Okay, so hydrogen fuel cell we'll talk about. So this is very interesting point. At low temperature, operates at low temperature. What happens? Anything that operates at very high temperature, definitely its durability will go down. Right, at high temperature there will be deterioration of the equipments or parts that is attached with that fuel cell. Definitely it will deteriorate. So if it is on long run at high temperature, definitely its durability will go down. Hydrogen fuel cell operates at low temperature. So low temperature operation improves the durability of any source, not only fuel cell. So power quality also remains same in the sense that deterioration is less. So if you see battery, as I mentioned, battery, if we continuously, when you have inverter battery at your home, okay, do you know what is the most important point to save your battery? The two things that you need to maintain about battery. If you want to take care of your battery, what is the main thing that you need to take care of? Repetition of charging. Okay, fast charging and repetition of charging or discharging means multiple time charging, discharging will deteriorate battery life. So that this is what here it is mentioned, that it is superior than battery because it is operating at low temperature and its power quality does not degrade over the time. Also it is tested at very extreme conditions. Okay, it's a lightweight unit, so durable than most of the batteries that I Fast refueling, that as I already mentioned, that battery has to charge, it takes long time to charge. It's not a home battery. If it's a battery energy storage, it's a very big battery, that is, if it is discharged, it will take lot of time, lot of current to charge it, and that's why here it is continuous, there is a flow, so it's no problem. So reliability reduces maintenance cost. Okay, so I talked about this storage. It acts as a storage. So what it says, that what it needs, I will explain in next slide. So if you can produce hydrogen, it will produce it will produce water. That water you can convert into hydrogen and oxygen, and that can be fed to the fuel cell, and it can generate power. So by using renewable energy, you can do this, and hence this does not, it can be a sustainable solution. It can run standalone. You don't need any other power source to run it. So like that, it can be a power storage thing. Okay. Scalability, this is also a very important factor. Okay, scalability. Let's say today what happens, what is scalability, let me explain you. What happens in my native place, beside my home there was a transformer. Okay, distribution transformer was there. Now that time the number of homes were less, and also number of the amount of power consumption was also less. That time barely 1 or 2 homes were having AC. Now almost every home is having AC, and almost every home, maybe multiple ACs are also there. So power has increased. So because of that, and also now number of homes are increased. So because of that, what they are doing is they have installed 2 more transformers. So because of that, the amount of space that you are going to get is more, right? So scalability, you are doing what you are doing, you are connecting them in parallel to increase the power level. So here the scalability is, here you have small power cells, and you connect them in series and parallel, and you can have big power in it, so that it can generate power at the desired output power level. So if you need more power, you can keep adding the power cells and to make more output power. That is called fuel cell stack. We'll come to that, fuel cell stack. Okay. Now this is here I will mention about how fuel cell module or fuel cell power cell, how it works. So what we have is, on one side there is a hydrogen flow, on one side there is a air flow. So actually what we need is, we need oxygen from air. So we need arrangement for that. So there is channel for hydrogen flow, there is a channel for air flow. Now when it comes, okay, this hydrogen has to be, this is one of the challenge that you have here. The hydrogen has to be very pure. Okay, 99.99% pure kind of hydrogen that you need, that is the fuel to this fuel cell. Now there is air flow, from air you have to extract oxygen. Okay, so these 2 layers are called gas diffusion layer. These are porous and conducting layer. Okay, porous means gas has to pass through it, and why electrical conducting? Because electron has to pass through it. Okay, in both the cases electron has to pass through it, so that here you will see. So then what we have is microporous layer. The function of this is like coating. This is like a coating on the GDL, gas diffusion layer. 2 coatings will be there. The function of this is these are the 2 electrodes. It try to distribute this gas throughout the surface area. This 1 dimension I am showing, it is actually 2 dimension. The function of this microporous layer is to distribute the gas all throughout the electrode, so that this chemical reaction takes place properly. Now these are the electrode catalyst. So here So, these are the two electrodes plus and minus, and this is the electrolyte. Okay. So, how it will work, that I will come to that. So, these are the two electrodes plus and minus. Now, let us see how it works. So, hydrogen is coming, then oxygen is coming, and then, so what it does is, here the electrons leave this positive plate and it goes through the load. So, hydrogen comes from here, and then this electron leaves from here and it passes. So, there are two channels, one is through the electrolyte and one through the load. So, electrolytes allows the positive ions only. So, hydrogen passes through it and then electron passes through, which is our need. Electron is not allowed to pass through that electrolyte, it passes through the load, and that is how we are getting the electrical power. So, and then it comes in contact with oxygen, and then with the electrons are accumulated here, and then what we are getting here, then electricity we are generating, and then water and heat we are generating. So, this is the process is going on inside a fuel cell unit, a fuel cell module. This process is going on. So, hydrogen continuous, there is a flow of hydrogen, and continuously there is a flow of water. This is not water, it is hot air. So, it is water vapor. Okay. So, what happens? So, the same thing that is mentioned here, power generation by combining H2 and O2 at the electrodes. So, in H2 is split into H plus and E minus at anode, and H plus through the electrolyte membrane to reach cathode. In cathode, it mixes with electron and oxygen to produce electricity, water and heat. Okay. It is an electrochemical process producing electricity continuously when your flow is continuous, but we will see it depends on how much electricity is produced, that depends on the flow of hydrogen as well, how it depends. So, these are the two equations. Chemical reaction is taking place, and this is the energy which is utilized. So, this mole converted into per mole, this kilojoule per mole is converted into heat and electricity. So, if we take heat and electricity together, then its efficiency is more, but if we take only electricity, then its efficiency is low. So, these are the equations. Okay. So, here from here the thing that we need to look into, it is generating a voltage of 1.23 volt, okay, which is not sufficient. Even that is under open circuit condition. When you are loading anything that you load, the voltage comes down. This you must be knowing, because there will be some internal impedance, and when you increase current, definitely there will be a drop and there will be decay in the voltage as well. So, this is the open circuit voltage, and therefore, how it can be improved? That is why we talk about fuel cell stack. In fuel cell stack, so this voltage comes down to 0.7 volt. Okay, when you are loading the fuel cell, this voltage comes down, further it comes down. So, we have to connect them in series and parallel. So, single fuel cell voltage and current is not sufficient. So, most of the practical applications. So, 1.7 volt, what will you do? So, for reasonable voltage, multiple fuel cell units connected in series parallel, so that is what I was talking about. You can scale it up. Okay. To necessary voltage and current level, you have to connect them in and make a fuel cell stack. So, people will say that, okay, this is 1 kilowatt fuel cell stack of 24 volt or 30 volt or 48 volt, like that. This is called fuel cell stack. So, generally it is not less than 50, it is more than 50. Okay, number of these are very thin, and you can connect them in parallel with bipolar plates. There are bipolar plates in between, because one cell is there and then another cell will come in contact with it. So, you must have bipolar plates, so that you can connect them in series. Now, efficiency of fuel cell. So, if conventional power flow we can see here. So, conventional power fuel flow is there. Let us say a conventional thermal power plant, if we see. So, what happens? The fuel comes and then there is a combustion. From that we generate steam. That steam is rotating the steam turbine. The steam turbine is associated with a rotating generator. That generator is producing So, efficiency, every stage there is a loss. Whenever there is a multiple number of stages, definitely your efficiency will come down. Why? Because if you, let us say 90% efficiency of one stage. So, if you have 5 stages, so you multiply 0.9, 0.9, 0.9, so efficiency subsequently go down. Okay. But in fuel cell, if you say, so here you have only chemical energy and then it converts into electrical and thermal energy. So, efficiency is 40 to 60% when you consider both electrical energy and thermal energy. Sometimes there is a need for co-energy, okay, co-energy generation. So, you want electrical energy, you want thermal energy, you can use it, and means there you can utilize both heat and as well as the electrical energy. Now, here you can see this is the characteristics voltage versus current density. Now, you see here the voltage is coming down when you are loading, the voltage is coming down. So, here ohmic region it is almost linear. So, resistance is constant. As you are increasing current, there will be a subsequent drop, and there the voltage from the fuel cell will come down. So, this is the voltage of a fuel cell stack. So, generally if you operate, let us say at 30 ampere, if you 30 ampere, so you will get 33 or something voltage. Okay. So, this is how much wattage you will get then? 33 volt and 30 ampere, around 1 kilowatt. Okay. So, 1 kilowatt fuel cell with 30 ampere output and 33 volt that you can use. Okay. Now, if you change the flow rate, if you change the flow rate, subsequently the voltage and the power level also changes. Okay. Voltage and so if you see here, the fuel cell, the power, the flow rate, if we are changing, we can see here we have plotted this in MATLAB. In different papers you will see there is a significant difference, but this is plotted in MATLAB, and there we can see that the difference is not that significant, because for the presentation purpose we may show that there is a significant difference, but actually there is a difference. Okay. Now, because of this power difference, so you have to have what? You always have to follow the maximum power. It is like maximum power point tracking we do for what? We do for maximum power point tracking, do you know? PV, then wind, then for hydropower plant, mini hydropower plant. Okay. So, everywhere when there is a change in when there is a change in power with some input parameter, you have to track that point, the maximum point. So, always you have to have something along with the power source, so that you can track the maximum. It is not like that you cannot generate power, but you need maximum power. You have to utilize the full power. That is why there is a need for maximum power point tracking. So, these are the losses that we have mentioned here, this activation loss, ohmic region loss. So, what are these losses? That let me explain you. So, activation loss is majorly due to it happens in the electrode surface. So, slowness when reaction, it is a chemical reaction. When there is a slowness in chemical reaction, so you need some energy to speed up, so drive the electrons. So, there is an activation loss. Ohmic loss is due to, there will be definitely, since there is a conducting path, nothing is, even if it is a superconducting coil, there is a resistance. You cannot avoid resistance, you have to come with that, you have to work with that. So, there will be definitely an inbuilt resistance will come into picture. Okay. Since the output of a fuel cell is DC, so we are talking about resistance. Why we are not talking about inductance in that case? Inductance will be there, right? If it is a wire is there, definitely there will be a resistance, there will be an inductance. So, why we not talk about inductance there?
Negligible there?
No, negligible may not be the reason. Okay, maybe it is negligible, but because of that, because we talk about steady state. Under steady state, an inductor behaves, when it is a DC circuit, under steady state it behaves like a short circuit. Okay. Okay. So, other concentration losses and fuel crossover losses are there. Okay. So, this is like if you have a model a battery, you have seen for battery also we do a modeling like that, capacitor and then resistor and all, and this model gives you because everything we have to model. Why we have to model? Because we need to know its dynamic performance. Because of that, we need to know anything, we need to model. A transformer, we model it. Okay. A high frequency transformer, we model it. Every equipment we have to model in order to understand it, the behavior of it, and so that how closely we can relate its behavior using that model. This model may not be unique. This model is mentioned in this paper. There could be several other models. You can also come up with your model, so that it should be as close as possible. Because why I am telling this model, maybe this model is suitable, but it might happen that how we are calculating this R activation loss, R ohmic loss, R this mass transport related loss, this measurement or this estimation could be different in different method. Okay. So, that is why you can have n number of models. Okay. Now, fuel cell rating. Okay. So, here just I want to mention you, in fuel cell is a like PV also, it's like current is high, voltage is low. Okay. So, when there is current is high, voltage is low. Okay, we will come to that. Just let me just tell you one thing. So, you can see here the only major thing that you need to look into, there are fuel cell system from 10 kilowatt, 2 kilowatt per cell is also available. Okay. There are multiple fuel cell suppliers are available. If you search over internet, there are suppliers. Okay, they can supply. So, they can supply up to, there are fuel cell industries are supplying commercially available up to 250 kilowatt, and you can connect to the grid as well. They will provide the fuel cell stack and also will provide the necessary converter along with it. Okay, it's a ready-made solution, install it, and one of the major thing is, one is there is no emission. Okay, let us say we have a diesel generator, as sir was mentioning, we have diesel generator at different parts of our campus. So, there are emissions, there are sound coming from that thing. If you replace them with battery, what could be the disadvantage? We can let us say same size box, we replace with battery box, multiple batteries connected in series, parallel, or whatever it. What could be the disadvantage? Battery, if it comes to battery. So, definitely there will be a degradation of the battery, and you need a good maintenance of a battery. Now, if you replace that thing with this thing, fuel cell, the first and foremost thing that you are going to have is its reliability is good, its efficiency is good. The third thing is its noise is very, very less, emission is not there. Okay. So, it will be there of same size, but you will have these advantages. Okay. Now, fuel cell applications, where people are using fuel cell. We talk about application of fuel cell in microgrid in this GIAN course, but fuel cells, you can see here, fuel cells are already people have started using and also proposing for, let us say, primary backup for power generation, commercial and industrial buildings, residential applications. Now, remote locations, at remote locations, okay, I remember somebody was mentioning that in some forest, okay, some research people see that some research person will be there who will be, let us say, going to Sundarban for, they are in research on different field, not electrical engineering, maybe on mangroves or something. They need power backup, definitely they need power backup. They cannot take what? Battery along with them, it's a heavy, right? It's a remote location. So, you need a lightweight solution. So, you can use this kind of thing. Okay. So, for remote weather stations, right. So, communication centers, rural area, remote research stations, you can use this kind of power backups. Large scale energy, so you can install at larger scale also. Automobiles are also there, definitely it is there, but these are power levels are less. But here the power levels are far more than when you are connecting to the grid. Distributed generation for microgrid application. Okay. Emergency power supply. Now, cogeneration, as I was talking about, so where you are both using both electrical energy as well as heat energy. So, in that case your efficiency is far more better than whatever a fuel cell when you are using for electrical energy. Okay. Now, power converter. Generally, what power converter that you are going to use for a specific power source, for that what you need to understand is first you need to understand what the power source is going to give me. Okay. The power source is a very crude. When you are taking oil from an oil field, you cannot take that oil directly, put in your vehicle and you can run it. Okay. What you need is you have to first process it. Before that you have to filter it. Okay. So, here also the voltage that it is generating, as I have shown you in the characteristics, that voltage, power, these are flow dependent, and also based on your current level the voltage is coming down and all. You have to take care of these things. So, no fixed voltage, current and power, and also it is flow dependent. So, you need what? So, output. Okay. Output requirements are what? You are using it for, let us say, for grid connection or for islanded mode or for, let us say, your home. So, what are the requirement that you have? It could be AC or DC. It could be grid connected, 3-phase, single phase, whatever it is. It can be standalone mode also. It can be in microgrid also. If it is microgrid, it could be AC, DC, micro, whatever it is. You have to connect it. So, what you need is you need a power converter. So, you need a power processing unit. So, the components of a power processing unit is, first and foremost thing is you need filters. Okay. Now, as I was mentioning about battery, in battery what happens? In battery, when you battery is a DC source. Battery behaves best when you take DC current or when you charge with DC current. Okay. So, like this, here also if it is a solar or if it is a fuel cell, these are not, you cannot charge it, only thing is you can discharge them. Discharge means you can take power from them, current from them. It is best if you take DC power from them, DC current from them. Okay. So, if you taking current which is having ripple, then it is better you use filter and filter it out, so that the current coming from the source is ripple free, or you minimize the ripple, so that the lifetime of the source will be improved. Okay. So, that is why there is a necessary for filter, passive filters. Okay. Passive filters are we prefer because passive filters are low cost and reliable. Definitely these passive things are reliable apart from capacitor, because capacitor is one of the most unreliable component in any equipment. Okay. Then at the output also you need filter, because you generate, when you have, it comes to power converter, we have bad name that power electronic engineers have a bad name that we are polluting the grid by injecting harmonics. Okay, we inject harmonics, but we use filters in order to reduce the harmonics. So, use filters so that the load does not know whether it is coming from an inverter, PWM inverter, or it is coming from utility supply. Then the heart of the thing is power converter. Okay, that power converter could be AC, DC, 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 whatever it is. Okay, since it is a fuel cell, it definitely will be DC to DC or DC to AC. Now, DC to DC converters are available. Okay. DC to DC converter, n number of research has been done and it is going on, still going on. So, DC-DC converters are there, but when it comes to DC to AC, direct conversion is not there, or there are, but generally what we use we use two stages. One is first you convert DC into suitable DC, and that DC you convert into AC using inverter. Then power converter comes with control unit, otherwise it will not work. A human body without brain won't work. So, you need a control unit. Then you need sensing unit. Okay, you have to sense. We have eyes, ears, nose, mouth, skin. These are the sensing units. So, here also, since it has to be a full system, it has to have a sensing unit at the input, at the output. In the input, I can say, like at the input, if you want to implement MPPT, the knowledge of current and voltage at the input side is necessary. Okay, that is why sensing unit. At the output side, you want voltage to be at certain level. So, the power converter need to know at what voltage level I am generating. I have to correct or not. I need to make it correct. I need to make correction or not. For that you need sensing unit. Okay. Then protection, as he was mentioning, definitely when we do at academics, this thing we forget about, that protection unit is necessary, EMI filters are necessary, but in industry these things are more important, because an industry, first thing that they look into cost, second thing is reliability. Okay. So, when it comes to a product, these three are the major thing that you need to look into. The protection, performance improvement using EMI, EMC filter and protection unit. These are far more important than anything else. Okay. And then communication. Okay. Now, when it comes to fuel cell, the things that we know that the output is DC in nature. It is a voltage and current, DC in nature. Voltage is low, current is high. Current should be ripple free or minimal to improve the life of the fuel cell, that I already mentioned. Power generation is flow dependent. That means if flow changes, then power generation will differ. So, you need MPPT. Okay. Now, here one question comes into my mind is, what should be the requirement? What should be the, now what kind of thing that you want to look into? Now, you need, so you have fuel cell, now you got the fuel cell. Now, you have to convert this fuel cell into, let us say you want to connect to the grid, or let us say you want to generate 230 volt AC for your home appliances. What you are going to do? What thing you are going to use here? How will you, what could be your idea? Just think what can be, what could be the solution. What is the first thing that you need? Okay, what is the gap? What is the gap? The power source is there, right? Now, what is the gap? You want to, let us say you want to run your television at your home. Yes.
The type of load we want to run.
TV I want to run.
Your DC. And what is the capacity of that load? Whether the input source will be able to supply or it is less or more. Accordingly, we have to control.
Yes, yes. So, the rating is important. Yes. Let us say the rating is sufficient to run your, let us say 1 kilowatt. 1 kilowatt is sufficient enough to run your measure of the home appliances. So, what first thing that you will do with this converter, with this power source? What you are going to use? Any converter that you need to use, right? Power converter. So, what power converter you want to use?
Depending on whether the load is DC operated or AC operated. If it is DC operated,
no, it's a television.
It should be fixed. If it is AC operated, then we have to convert.
So, if it is a television I mentioned, so that runs from AC, okay.
Yes.
So, in that case,
you have to convert it to AC then.
See, yes, you have to convert into AC. But the thing is, as I mentioned, this voltage is low, okay, this voltage is 33 volt, and at home the voltage that you need is 230 volt RMS. So, how we can convert them?
You have to first boost the voltage.
Boost converter, yes, absolutely correct.
DC to
absolutely correct. Boost converters, okay, correct.
Step up the DC voltage and then convert into AC.
Okay, okay, correct, absolutely correct. Now, the thing is, here the voltage is 30 volt or 33 volt, and you need a voltage level of around 400 volt. Okay, there are many things that you can do. Okay, but I will tell you why those are not feasible or may not. You can avoid it. At home inverter, I don't know how many of have lifted it. Have you lifted anybody home inverter? It's a heavy inverter. Have you seen inverter? Because it is having a low frequency transformer. Like a low frequency transformer we trying to avoid. Why? Because previously we had 5 volt DC sources, 5 volt adapters, where those were heavy. I remember we have at our home some music system. It is having an adapter which is very heavy, because it is having what this low frequency transformer. Now, SMPS chargers that you have, that is mobile chargers, those are SMPS chargers which are low in weight, because they don't have those kind of high frequency transformer. So, why not to convert this 33 volt DC directly to some high voltage DC, so that you don't need any transformer. So, normal boost converter to boost this voltage level to that higher voltage DC is not feasible. Just normal boost converter if you connect, that is not suitable. For that we need specific boost converter, that I will explain. But before that, let me tell you, since it is high current application, since this converter is going to supply you high current, it is 30 ampere for a high power level, it will be more. So in that case, the current has to be distributed so that the reliability and efficiency can be improved. Let us say at the converter that you are going to use here is having 30 ampere, the inductor is at the input, you have an inductor, the inductor has to carry 30 ampere. Now if you split it into two inductors, the two inductors will carry 15 ampere each. So in that case, you can reduce the loss, you can improve the availability, reliability of the system. So because of that, the converters that we propose, so this I will come, the converter that is proposed here are, this is floating dual boost converter, where, so this is one boost converter, this is one boost converter, this is another boost converter, so that it is twice, the gain of this converter is twice of boost converter. So we are trying to increase the boost, so that increase the boost value, so that we can increase the voltage output directly from the fuel cell. These converters are specifically, if you can see, state of art of DC-DC converter for fuel cell vehicles. So this is specifically to boost low voltage to high voltage, so that we don't need intermediate voltage, intermediate stages, and we can get higher output voltage, and we can generate the AC directly from the DC that we are obtaining. Okay. So the converters that we have here is, one is floating dual boost converter, where we have two boost converter, and as I was mentioning about the inductors, two inductors which can share the current. So these two are, so these are boost converters only, this is one pair, this is another pair. These are interleaf boost converter, where the ripple current can be reduced, I will tell you. So here two inductors will share the current, and also there is a ripple minimization technique by which you can reduce the current ripple delivered by this current source, by this source. Yes. Okay. So similarly, you have another which is floating double boost, double stage boost converter. So these converters are, so there are two stages, two stage boost converter, two stages, and then they are floating in order to make this. So they know that the output voltage of a fuel cell is less, and we need high voltage, and that is why we are using boost converter of higher gain, so that the conversion can be done without any intermediate stage, and directly you can convert into high voltage level, and this high voltage level you can use for conversion into AC. Okay. So there are different types of fuel cell, proton exchange membrane, and then direct methanol fuel cell, and these are the suitable. These actually all fuel cells are not suitable for standalone power generations. Okay. So there are specific fuel cell which are suitable for standalone power generation, and those are only we marked as suitable for distributed generation in case of microgrids. Okay, nothing comes free. Okay, everything comes with some. You cannot say that, okay, I made this and this is one of the best thing that we can have. It is not like that. Okay, everything comes with some issue. So it's first thing that we should associate with the fuel cell technology is it's expensive. Okay, it's very expensive currently. Okay, future maybe price may come down. Okay, but currently it is expensive. Okay. And hydrogen generation and storage is a difficult task. Okay, that's a very difficult task. And when you compare with other sources, you have to compare its. See, when it's a layman going to use your source, he doesn't know whether it is a battery, whether it's a fuel cell, whether it is a solar, whether it is a wind. He will compare whether like electric car and IC engine based car. When you sit on that, you don't think whether it is electric car, whether it is IC engine. You will see whether its performance is comparable or not. So here also, when you trying to compare it with other sources, there will be comparison of dynamic response. Its dynamic response is slow. Okay. So finally, we can conclude that it's a near future technology. Okay, people are working on it like anything, and in academics research are going on, and research we do in academics so that the things can be made practical and it can be made commercial. Okay. So, suitable stationary and transport application, people have already started using it. Continuous power generation and supply to load, hence more desirable for distributed generation. Continuous, it is there. Okay. Then PV and wind, it is very intermittent in nature, PV and wind. So, that is why we are looking for alternate sources. Okay. Efficiency we can say superior, we cannot say best, we can say superior. Carbon emissions are nearly 0, but this what I mentioned in last slide, that converting low voltage DC into high voltage DC is a challenge. Okay, that is a challenge with more number of components, costly in the current scenario. Okay. So, this is where I want to stop. Okay, few references are there. So, now I expect some question answers from online and offline participants. See, if it is 250 kilowatt, if commercially available 250 kilowatt, so it is either you use in islanded mode or it can be used for the grid connection mode also. Yes, it is available, commercially it is available, companies are proposing. Okay, it's already we late by maybe almost 1 hour. Okay, we can stop here. Okay, thank you everyone for joining with us, and we got delays, some delay we got. Okay, thank you for your patience. Thank you. We are closing now.
Thank you, sir. Thank you.
Thank you.
Thanks for interesting lecture.
Thank you. Thank you so much.